Hello there, and welcome to Physics with William, where curiosity gets cozy and science slows down just enough for us to actually look at it. Tonight we're heading into one of the smallest and strangest parts of the physical world, towards something that does not sit on a table, does not show up in ordinary life, and yet is built into almost everything around you. We're going to talk about quarks, not in the rushed classroom sense, and not in the way they sometimes appear in textbooks as a quick stop on the road to the next topic, but in the quieter and more honest sense. What is a quark, really? What kind of thing is it? Why do physicists say it is fundamental? And why, if it is so important, can it never simply show up alone like a pebble on a windowsill or a coin on a countertop? Before we get into that, I would love to know where you're listening from tonight. Are you winding down at the end of the day, half under a blanket with the room dark except for one small lamp? Or perhaps it is early where you are, and the day has only just started to stir. However, and wherever you are arriving here, I am glad you are here. And if this sort of slow walk through physics helps you relax, settle your thoughts, or just enjoy the company of an idea for a while, do consider liking the video and subscribing. It helps this quiet little corner of science reach more people who might need something calm to listen to at the end of a busy day. Now let us take our time with this, because quarks have a way of sounding simple for about 10 seconds, and then becoming deeply odd the moment you try to picture one properly. At first glance, the idea seems straightforward enough. A quark is a tiny building block of matter. That is the sort of sentence you might hear in a science video, nod along with, and feel satisfied by for a moment. But the trouble begins almost immediately, because the word building block invites a very specific image in the mind. It suggests something like a grain of sand or a little bead or a microscopic brick. It suggests a tiny thing with a neat edge and a stable identity, something that could in principle be placed on its own, pointed at, and described as this and only this. A quark does not fit that picture very comfortably. In fact, one of the first important things to understand is that the universe, at very small scales, does not behave like a box of tiny objects waiting to be lined up and counted. It behaves more like a deeply structured set of relationships, rules, and interactions. So when we call a quark a particle, that word is useful, but it also hides as much as it reveals. This is often the challenge with physics at the small scale. The language arrives from ordinary life, but the reality does not. We say particle, charge, colour, spin, flavour, and each of those words sounds as though it should connect neatly to everyday experience. Then you look closer and discover that none of them quite means what your first instinct hoped it meant. Physics is very good at borrowing familiar words and then giving them lives of their own. It is a bit like inviting a cat into your house and discovering 3 weeks later that the cat now owns the furniture and has renamed the living room. Still, there is a good reason physicists talk this way. Human language was not designed for the inside of a proton. We built it to talk about weather, trees, dinner, late trains, awkward conversations, and all the other things that insist on happening at human scale. So when science reaches down into layers of nature that no one can directly see, it has to make do with the words available. That is why, to understand quarks properly, we need patience. We need to be willing to hold a simple idea in one hand and then keep adjusting it as the details come in. A useful place to begin is not with quarks themselves, but with our long habit of thinking we have reached the bottom of things. Human beings have been doing this for quite a while. First there were objects around us, stones and leaves and bones and drops of water. Then came the thought that perhaps all of these things are made of smaller pieces. Much later, atoms emerged as the serious scientific answer. For a time, the atom seemed like the final stop, the indivisible unit, the thing beyond which there was nothing further to peel back. Even the name more or less announces the conclusion. It means something like uncuttable, a bold claim as it turned out. Nature has a long history of smiling politely at our confidence and then handing us a finer knife. When atoms were found to contain electrons and a central nucleus, the picture changed. Suddenly the atom was not the end but a kind of organised system. Then the nucleus itself was found to contain protons and neutrons. That felt for a while like another satisfying layer. Very small, very solid sounding, very tidy. Protons and neutrons looked like they could be the proper furniture of matter, and yet the story kept going. By the middle of the 20th century, experiments were revealing more and more particles, enough to make the situation feel almost untidy. If you have ever cleaned out a drawer expecting to find 3 useful things and ended up staring at 17 mysterious cables and a battery of unknown origin, you will know the general scientific mood. This growing zoo of particles was not comfortable. Physics tends to prefer patterns over clutter, so when more and more subatomic particles began appearing in experiments, it became natural to suspect that perhaps at least some of them were not fundamental after all. Perhaps they were made of smaller ingredients. That was the road that led toward quarks. Not as an act of whimsy, though the word itself is whimsical enough, but as a serious attempt to bring order to a mess of observations. Physicists noticed patterns in the properties of hadrons, which are particles such as protons and neutrons that feel the strong interaction. Those patterns hinted that these particles might be combinations of more basic ingredients. Quarks were proposed as those ingredients. Now at this stage there is a temptation to imagine the proton as a little bag with 3 marbles in it, each marble being a quark. This is understandable, and it is not entirely useless as a very first approximation, but it will need to be softened as we go. Because a proton is not really like a bag of hard bits sitting still next to one another. It is a far more active and less tidy thing. Even so, let us allow ourselves the first version for a moment. In the simplest picture, a proton contains 3 quarks. A neutron also contains 3 quarks, just arranged differently in terms of type. That simple statement turned out to explain a great deal. It was elegant, powerful, and promising. There was just one inconvenience. No one had ever seen a single quark by itself. That was awkward. It is one thing to propose unseen ingredients. Science does that often enough, and sometimes very successfully. But sooner or later the ingredients had better show some sign of independent existence. If you tell people that a cake contains flour, eggs and sugar, they tend to expect that flour, eggs and sugar can also exist outside the cake. They are usually less impressed if you insist the flour can only ever be encountered once baked, frosted and served on a plate. With quarks, however, that is rather close to the truth. Quarks appear in combinations. They shape the particles we can observe. They influence measurable outcomes in experiments. They leave fingerprints all over the data. But isolated quarks do not step out into the open on their own. This is not because we have not tried hard enough. Physicists have tried very hard indeed. So what is a quark, if it is real but never solitary? The best answer is that it is a fundamental excitation of a quantum field, carrying certain properties that allow it to participate in the strong interaction, and to combine with other quarks into larger particles. That is a more accurate answer, though not yet a very comfortable one. The phrase quantum field is doing a lot of work there, and we will not burden the evening by trying to unpack every corner of it all at once. For now, the important part is this. A quark is not best imagined as a tiny bead. It is better understood as one of the basic forms that matter can take at the deepest level we currently know, a basic constituent with a set of well-defined properties, but one that only ever appears in company. Those properties matter enormously. A quark has mass. It has electric charge, though in values that are unusual compared with the charges of familiar particles. It also has a property called color charge, which despite the name has nothing to do with visual color. No tiny reds or greens are splashing around inside your coffee mug. This is one of those borrowed words I warned you about earlier. The term color here belongs to the mathematics of the strong interaction. It is a label used to describe how quarks behave under the force that binds them together, and that force is the key to the mystery of why quarks cannot exist alone. If this all sounds a little unfair, you are not alone. Many students first meeting quarks feel mildly betrayed by the setup. First they are told that quarks are basic ingredients of matter. Then they are told that no one can pull one out and inspect it in isolation. Then they are told that the force between quarks actually gets stronger as you try to separate them. This seems almost rude on the part of the universe. Most things become easier to separate when you pull on them. A drawer opens, a zipper parts. Two magnets may resist at first and then come away. Quarks respond differently. In a very real sense, trying to isolate one only pours more energy into the system until that energy becomes enough to create new particles, leaving you with combinations again rather than a lonely quark sitting on the table looking embarrassed. That behaviour is so unusual that it changes the very tone of the subject. We are no longer just dealing with smaller and smaller pieces in the ordinary sense. We are dealing with a domain where the rules of interaction do not merely connect the pieces. They define what kinds of pieces can show up in the world as separate things at all. A quark is fundamental, yes, but it is also confined. And that word, confined, is one of the most important in the whole story. It does not mean hidden because of limited instruments, as though somewhere in the future we might finally build a sufficiently fussy machine and scoop up a free quark in a jar. It means something deeper. According to the theory we use, the strong interaction confines quarks so thoroughly that isolated quarks are not part of ordinary observable reality. This makes quarks a marvellous example of how nature can defy our instincts while still being precise. We tend to imagine that understanding means reducing something to pieces and then laying those pieces out plainly. But here the pieces refuse the plain layout. They are knowable through theory, through experiment, through patterns, through scattering results, through the structure of matter itself, yet not knowable in the simple hold-it-in-your-hand sense. There is a lesson in that, and it is one physics teaches again and again. Reality is under no obligation to be arranged according to the habits of common sense. Common sense was built for crossing roads and opening doors. It did not evolve for the inside of atomic nuclei. Even so, quarks are not just theoretical decorations. They are as serious as physics gets. The proton that helps make up the nucleus of every ordinary hydrogen atom is a quark-based object. The neutron in heavier nuclei is another. Much of the visible matter around you depends on the existence and behaviour of quarks. The body listening to this, the walls around you, the planet beneath you, all of it rests in part on what quarks do together. There is something quietly astonishing in that. We live in a world of tables, trees, oceans, weather, cities, voices and memories, and underneath much of the solidity of that world lies a kind of restless subatomic social arrangement in which some of the most basic constituents are never permitted to go off on their own. It is also worth noting that quarks do not all come in a single kind. There are several types, usually called flavours, another charmingly casual word for something very technical. Some are common in ordinary matter, and some appear only in more extreme circumstances or for very brief times in high-energy events. But tonight, in this opening stretch of the journey, what matters most is not memorizing the list. What matters is feeling the shape of the problem. A quark is a basic constituent of matter. It has definite physical properties. It helps form larger particles. It is real in the strongest scientific sense. Yet unlike something like an electron, which can exist on its own, a quark is never found alone in ordinary conditions. That combination of basic and never solitary is what makes quarks so fascinating, and perhaps that is why the subject often captures people once it gets past the first layer of technical language. Quarks are not merely small. Small is easy. Dust is small. A breadcrumb is small. A typo on a phone screen is sometimes small enough to escape detection until the message has already been sent, which is its own branch of particle physics. No, quarks are interesting because they force us to update what we mean by an object. They live at the point where matter becomes inseparable from interaction, where the identity of a thing is tied not only to what it is, but to how it must remain bound to others. You can feel the broader philosophical temptation here, and I will resist it just enough to remain useful. Still, physics sometimes gives us facts that carry an almost accidental emotional resonance. The quark is one of them, a fundamental thing that cannot stand alone, a constituent of matter that only appears in lasting combinations, a piece of the world that becomes visible through relationship. One does not need to turn that into poetry to notice that it is an unusual and memorable feature of the universe. Nature could have been built differently. It could have offered us neat independent units all the way down. Instead, at this level, it gives us confinement, combination, and a force that binds more fiercely when separation is attempted. As we move further into this story, the next step will be to back up slightly and look again at the atom, because to understand why quarks were needed at all, it helps to see how the older picture of matter began to crack open under closer investigation. We will need to visit electrons, nuclei, protons and neutrons, and then ask why even those familiar names turned out not to be the final answer. From there, the ground becomes firmer. Once you see how the proton stopped being a solid little dot and became a busy interior world, quarks start to feel less like a strange add-on and more like the next honest step. And that is where the road naturally leads from here, from the comforting old image of the atom as a final tiny object toward the deeper and less comfortable realization that the atom was only ever the doorway. Now, if we're going to understand quarks properly, we need to rewind a little and look at the atom again, because the atom has had a remarkably successful career as the supposed end of the story. For a long time it was presented that way, and to be fair, it earned the reputation. The atom explained chemistry, it explained why substances combine in fixed ways, and it gave matter a kind of underlying order that people had suspected for centuries, but had never been able to prove in a modern scientific sense. Once atoms became real scientific objects rather than philosophical guesses, it felt as if the world had finally revealed its smallest proper pieces. Matter, it seemed, was made of atoms, and that was that. There is something very satisfying about reaching a smallest thing. The mind likes a bottom floor. We like to imagine that if we keep taking things apart, eventually we will arrive at units that simply are what they are and need no further explanation. It gives a sense of closure. It makes the universe seem organized, almost tidy. A table is made of wood. Wood is made of molecules. Molecules are made of atoms, and atoms are the final little beads of reality. You can almost hear the drawer sliding shut. The only problem, of course, is that nature did not agree to stay tidy for our convenience. Even the word atom carries a bit of misplaced confidence. It comes from the old idea that this thing could not be cut further. That was the promise built into the name. It was an ending disguised as a noun. But as experimental physics improved, as instruments became more precise and more imaginative, the atom stopped looking like a final object and started looking more like a structure. And that change matters, because once the atom became a structure, it was no longer the foundation itself. It was something built from deeper ingredients. This shift did not happen all at once. Science almost never moves by one dramatic curtain pull where the whole set changes in an instant. It moves more often by discomfort. Something in the existing picture stops behaving as expected. A result looks odd. A beam scatters in a way it should not. A number arrives that does not fit. At first, people try to patch the old view, which is understandable. Nobody wants to throw out a working framework lightly. But eventually the little discomforts begin to gather, and once enough of them are sitting in the room, pretending nothing is wrong becomes more exhausting than changing your mind. The atom began to crack open in that exact way. Early models treated it as a kind of indivisible unit, but then came evidence that atoms contain smaller charged components. Electrons appeared first in that sense, not literally in history as tiny creatures emerging from behind a curtain, but as real measurable parts of atomic structure. Suddenly the atom was no longer a single undivided object. It had pieces, it had an internal arrangement. Already the name was looking a little overconfident. Once electrons were in the picture, a new question emerged. If atoms contain negatively charged electrons, what balances that charge overall? Since ordinary matter is usually electrically neutral, there had to be positive charge somewhere as well. That led to the idea of a concentrated centre, a nucleus, and this was confirmed in one of the great moments in physics when experiments showed that most of the atom is empty space and the positive charge is packed into a tiny dense core. That revelation alone was startling. The atom, which people had once pictured as a compact little object, turned out to be mostly emptiness, with a dense nucleus at the centre and electrons existing in a more spread out arrangement around it. If you had grown attached to the idea of solid miniature balls, this was not a comforting development. The furniture of reality was becoming less furniture like by the minute. Still, for a while, the nucleus seemed promising as the new endpoint. Very well, perhaps the atom is not fundamental, but the nucleus is where the real solidity lives. The nucleus is dense, central, important. Surely that is the place where the story bottoms out. And again, for a while, this seemed plausible. Then the nucleus itself was found to contain parts. Those parts were protons and neutrons. By the time they came fully into focus, the atom had been thoroughly demoted from final building block to organised system. Matter was now understood in a more layered way. Atoms contain electrons and nuclei. Nuclei contain protons and neutrons. It was a more complicated picture, but still a manageable one. In some ways, it was even more satisfying. Instead of one mysterious indivisible unit, physics now had a small cast of characters with clear roles. Electrons were light and negatively charged. Protons were positively charged and lived in the nucleus. Neutrons lived there too, carrying no electric charge. This explained a great deal. It gave structure to the periodic table. It clarified isotopes. It helped make sense of radioactive processes. Once again, it was tempting to declare victory. Perhaps now, finally, we had the true ingredients. And to be fair, protons and neutrons do feel like the sort of things one could happily mistake for fundamentals. They are substantial enough by particle standards, central to ordinary matter, and easy to treat in basic models as if they were self-contained objects. If you learn introductory atomic physics or chemistry, that is often more than enough. You can go a very long way in science without worrying about whether the proton has an internal life. For many purposes, it behaves just fine as a single particle. That is one reason the deeper story stayed hidden for as long as it did. Nature often allows useful approximations to work beautifully, right up until you ask a sharper question. And sharper questions were exactly what physicists began asking. One of the most important tools in modern physics is the idea that to learn what something is made of, you do not merely stare at it. You hit it with something, preferably in a very controlled and highly intelligent way. Human curiosity has a surprisingly large overlap with the behaviour of a raccoon investigating a locked container. We jiggle, poke, shine light, send beams, and see what comes back. At the subatomic level, this becomes scattering experiments. You fire particles at a target and study how they deflect. The pattern of that deflection reveals something about the internal structure of the target. This is how the nucleus itself was discovered as a compact centre inside the atom, and later the same general logic was used again at smaller scales. If a proton were truly a simple solid dot with no interior, then very high energy probes aimed at it should scatter in one kind of way. But if the proton contains smaller constituents, the scattering pattern should reveal signs of inner structure, and that is exactly what happened. When energetic electrons were sent into protons, the result suggested that the proton was not an indivisible object. It behaved as though there were smaller entities inside carrying momentum and charge. Not only that, but the details matched a growing theoretical picture that had already been forming from another direction. Physicists studying the bewildering collection of particles produced in high-energy experiments had begun to suspect that many of those particles were built from more basic components. The proton and neutron, far from being final units, appeared to belong to a larger family of composite particles. This was one of those moments when two roads in physics met very neatly. On one road, scattering experiments were hinting that protons had internal constituents. On the other road, the zoo of discovered particles was crying out for some underlying order. Put those together, and the idea of quarks became much more than an elegant guess. It became a powerful organizing principle. But before we get fully to quarks themselves, it is worth lingering for a moment on how strange this history is from a human point of view. We keep finding a level that seems final, then discovering that it has deeper structure. It happened with matter in general, then with the atom, then with the nucleus, then with the proton and neutron. Each time the mind says surely this must be it, and each time nature raises an eyebrow and offers one more layer. There is a humility in that pattern. Physics is not merely a list of discoveries. It is also a long education in how cautious certainty ought to be. At the same time, the story is not one of endless collapse into chaos. Each deeper level brought more clarity, not less. Discovering that the atom had parts did not make matter incomprehensible. It made it more understandable. Discovering that nuclei contained protons and neutrons did the same, and discovering that protons and neutrons are themselves composite also turned out to be a gain in understanding, not a loss. What first looks like complication often becomes explanation once the pattern settles. That pattern was badly needed by the middle of the 20th century, because particle physics had become rather crowded. Experiments were uncovering more and more particles, especially in cosmic rays and later in accelerators. Some were short-lived, some more stable, some came in families with curious regularities. It started to look less like a clean set of fundamental objects, and more like an overcrowded guest list. This is usually the point at which physicists become deeply suspicious. When nature seems to be offering too many supposedly fundamental particles, it is often a sign that some of them are not fundamental at all. Think of chemistry before the atom was well understood. If you did not know about atoms, molecules might look like unrelated substances with no deeper connection. Water, oxygen, methane, carbon dioxide, each its own thing. But once the atomic view arrives, a great deal of that variety is revealed as combination rather than true fundamental diversity. Something similar happened in particle physics. Many of the newly discovered particles began to look less like separate basic units, and more like different arrangements of a smaller set of ingredients. This is where the proton had to lose its status as a final object. Not because it stopped being important, but because it started making more sense as a composite one. The same with the neutron. They were no longer to be treated as indivisible stones at the base of matter. They were structures held together by something deeper. That something deeper had to explain several things at once. It had to account for the known properties of protons and neutrons. It had to fit the patterns seen across many related particles. It had to work with scattering evidence showing substructure. And it had to make sense within the broader framework of quantum physics, where particles are not little billiard balls but excitations with precise measurable properties. Quarks answered that need. At first, this did not mean that quarks were immediately accepted as ordinary little objects hiding inside hadrons, which is the family that includes protons and neutrons. There was caution, and rightly so. A good theory must do more than sound clever. It must match observation. It must survive contact with experiment, which is where many beautiful ideas go to lie down. But quarks kept proving useful. They explained patterns in charge, spin, and classification. They made sense of the data in a way the old picture could not, and yet there remained a deep oddity. If protons and neutrons are made of quarks, where are the individual quarks? Why do they not show up alone? Why do detectors not simply find them wandering about independently, the way electrons do? This was not a minor side question. It went straight to the heart of what kind of thing a quark is. This is one reason the atom matters so much in the story. The atom teaches us that what looks fundamental may be structured. But the quark teaches an even stranger lesson. It says that the deeper ingredients are not always available as separate everyday objects. The step from atom to nucleus to proton is a story of uncovering smaller pieces. The step from proton to quark is more subtle. It is the discovery of smaller constituents whose existence is real, measurable, and indispensable, but whose isolation is forbidden by the very force that defines them. So when we say the atom is not the end of the story, we do not simply mean that there were more pieces inside. We mean that the whole logic of matter changed as the investigation went deeper. The atom gave way to a layered structure. The proton gave way to internal constituents, and those constituents did not behave like little beads waiting to be poured onto a tray and counted in peace. They belong to a world where interaction is not an accessory to identity. It is part of identity from the start. That is why this journey matters. It is not only a history of smaller and smaller scales, it is a gradual correction of the imagination. At first we picture matter as objects made of smaller objects made of smaller objects, all the way down like a set of Russian dolls. But the deeper picture is less comfortable and more accurate. The dolls are not always doll-shaped. Some of the innermost ingredients cannot simply be lifted out and admired. Some are known through the patterns they create, the combinations they form, and the rules that prevent their separation. Even the familiar word particle becomes slightly strained by this point. It still works, but only if we remember that a particle in modern physics is not necessarily a tiny hard thing with a fixed edge. It is better thought of as a quantized entity with specific properties, something that appears in interactions in lawful and measurable ways. Once you make that adjustment, the path from atom to quark becomes clearer. The atom was not the end because matter is not built in the simple visual language our instincts first prefer. Still, the old atom deserves some respect. It was not wrong, it was incomplete. And this is one of the healthiest distinctions in science. Older models are often not false in the everyday sense. They are limited. They work within a range, then fail outside it. Chemistry still works beautifully with atoms. Basic nuclear physics still works beautifully with protons and neutrons. But when you probe deeply enough, when you ask what those protons and neutrons are, the older level stops being enough. So the atom remains a useful truth, just not the deepest one. And that takes us very naturally to the next question, because once the atom has stepped aside as the final answer, and once the proton has done the same, we are left facing the object that has been waiting quietly behind both of them. If protons and neutrons are not the end, then what exactly is sitting underneath them? What kind of thing is a quark, really, when you strip away the textbook shortcut and ask the question slowly? So now we have reached the point where the proton steps slightly out of the way, and the real question moves to the front. What is a quark, really? Not the quick classroom answer, not the tiny bullet point that says quarks are the things protons and neutrons are made of, but the slower answer. The kind of answer that actually helps the mind settle around the idea, instead of just repeating the word and hoping it starts making sense on its own. A quark is one of the most basic known ingredients of matter. That is true, and it is a good place to begin, but it is still only the beginning because the phrase basic ingredient makes the mind reach for the wrong image almost immediately. It makes us think of crumbs in a loaf, or nuts in a cake, or pebbles in a jar. It makes us picture little hard pieces with edges and surfaces, each one quietly sitting there being itself. That picture works well enough for marbles and raisins and missing buttons found under the sofa. It does not work very well for quarks. A quark is not a tiny object in the ordinary sense. It is not a miniature grain of anything. It does not have a little shell and a tiny surface that you could imagine touching if only your fingers were absurdly more ambitious than biology intended. When physicists call a quark a particle, they're using the best available word for something that behaves in certain definite ways during experiments. The word is useful, but it has limits. At very small scales, matter stops behaving like a collection of little solid bits and starts behaving according to the rules of quantum physics. That means the things we call particles are better understood as basic physical entities with measurable properties that show up in interactions, rather than tiny everyday objects scaled down billions of times. This matters because when people first hear the word quark, they often try to picture a proton as a kind of small container with 3 tiny beads rattling around inside it. That picture is not completely useless as a first step. It points in the right direction. A proton does contain quarks. A neutron does too. But the picture becomes misleading if you hold on to it too tightly. Quarks are not really like peas in a pod. They are part of a quantum system that is active, restless, and held together by a force that behaves very differently from the forces we meet in ordinary life. So perhaps the cleanest first statement is this: a quark is a fundamental particle that carries mass, electric charge, and a special kind of charge related to the strong interaction, and it combines with other quarks to form larger particles such as protons and neutrons. That sentence sounds technical because it is technical, but each part of it can be unpacked in a simple way. When we say a quark is fundamental, we mean that as far as our current best theories can tell, it is not made of smaller ingredients. This does not mean science will never revise that view. Science has changed its mind before, and often for good reason. But within the standard model of particle physics, quarks are treated as elementary. They are not thought of as little bundles of something else. They are among the deepest level of matter currently known. When we say a quark carries mass, we mean it contributes to inertia and to the properties of the larger particles it helps make. Though here the story becomes a bit surprising again, because most of the mass of a proton does not come simply from adding up the masses of its quarks in the ordinary common sense way. Much of the proton mass comes from the energy of the motion and interactions inside it. This is one of those details that quietly changes your view of matter. The mass of everyday visible stuff is not just a pile of tiny little masses stacked together. It is heavily tied to energy bound up in the motion and force fields inside particles. So even before we get lost in the stranger parts of the story, quarks are already warning us not to expect the world to behave like a set of nested Russian dolls. Then there is electric charge. Quarks carry electric charge, but in values that are unfamiliar if your mental reference points are the electron and proton. Some quarks carry a charge that is 2/3 of the proton charge, and some carry a charge that is minus 1/3 of the proton charge. This sounds odd at first because many of us meet electric charge in school through a very simple picture where charges seem to come in neat whole units. Quarks quietly ignore that expectation. This is not a mistake or a trick. It is simply how nature is arranged at that level. The larger particles built from quarks, such as protons and neutrons, end up with whole charges when the quark charges combine, and that is one reason the system works so neatly, even though the pieces themselves seem unusual. Still, if quarks had only mass and electric charge, they would not be nearly as strange as they are. The deeper oddity comes from the strong interaction. Quarks carry a kind of charge that belongs to the strong force, usually called color charge. This has nothing to do with visual color. Nothing inside a proton is literally blue or red in the way a painted door or a traffic sign is blue or red. The word was borrowed because physicists needed labels, and the labels had to help track how quarks combine. It is useful language, but it is also one of those places where physics sounds as though it may have been named by a very clever person who had been awake too long and had started finding the whole thing amusing. Color charge is what makes quarks participate in the strong interaction, which is the force that binds them together. This is the most important feature of a quark if you want to understand why quarks are never seen alone. The strong interaction is not just another version of magnetism or gravity. It behaves differently in a crucial way. Most forces we're used to grow weaker as things move farther apart. Gravity weakens with distance. The electric force does as well. But the force between quarks does not simply fade away in that familiar manner. In fact, as quarks are pulled apart, the interaction does not become easier to overcome. It becomes stronger. That single fact changes everything. Because of this, a quark is not just a fundamental particle. It is a confined fundamental particle. It is a basic ingredient of matter that nature does not permit to drift around freely under normal conditions. That is why quarks are so hard to picture. If electrons were like quarks in this respect, electricity would be much less convenient and probably far more dramatic. Fortunately for our homes and devices and ability to charge annoying things overnight, electrons are allowed to exist alone. Quarks are not. This leads to a useful correction in how we imagine the inside of a proton. A proton is not a box with 3 tiny objects sitting still inside it. It is more like a tightly bound quantum system in which quarks are constantly interacting through particles called gluons. These gluons are the carriers of the strong interaction. They are not mere messengers passing notes and leaving politely. They are part of the system itself, and they can interact with one another too, which makes the strong interaction richer and more complicated than the electromagnetic one. Inside a proton, then, there is constant activity. Quarks exchange gluons. Energy moves through the system. Quark and antiquark pairs can briefly appear and disappear as part of the quantum behavior of the field. The proton is not a static object. It is busy. That word busy may sound informal, but it is actually useful here. People often imagine that fundamental physics must become cleaner and simpler as you go down in scale. In one sense it does, because the rules become more precise, but in another sense it becomes more dynamic. The proton at first seems simpler than the atom because it is smaller, yet when you look inside it you do not find a neat, quiet interior. You find motion, interaction, and a kind of organised subatomic traffic that is lawful but far from still. So what is the quark in that system? It is one of the matter particles that gives the proton its identity. In the simplest description, the proton contains 3 quarks, known as valence quarks. Those are the ones that set the basic overall properties. But around and within that simple description lies a more complicated sea of activity involving gluons and temporary quark-antiquark pairs. This is why one must be careful with the statement that the proton is made of 3 quarks. It is true in the basic classificatory sense, but the full internal picture is more active than that sentence suggests. Even with all of this, we can still say something very direct. A quark is not just a theoretical convenience. It is not a mathematical ghost invented to patch over awkward data. Quarks are real in the same sense that any successful physical entity is real. They reveal themselves through experiments. They explain scattering results. They account for patterns in particle behaviour. They are required by the theories that have passed test after test with extraordinary accuracy. Their reality is not the reality of a pebble in your hand. It is the reality of something whose presence is established by consistent, measurable effects. This may sound obvious, but it is worth saying because there is a recurring trap in discussions of physics. People sometimes assume that if a thing cannot be seen directly or isolated neatly, it must somehow be less real. But much of science works by inference from effects. We do not directly see gravity as an object. We see what it does. We did not know the deep structure of the atom by peering inside one with a tiny ladder and a flashlight. We learned by studying patterns, measurements, and outcomes. Quarks belong to that same serious tradition of science. They are not guessed at carelessly. They are inferred with discipline. Another important part of what a quark really is comes from how it fits into the wider family of matter. In the standard model, quarks belong to a class called fermions. These are the matter particles, the ones that make up the material content of the universe. There is another class of particles that carry forces, and gluons belong there. So quarks are the matter side of the story. They are constituents. They are building elements. But unlike electrons, which also belong to the matter family, quarks participate in the strong interaction. That strong interaction is what makes them group together into hadrons, which include protons and neutrons. This is one reason the proton and neutron are not fundamental, even though they are so important. They are composite hadrons built from quarks. In contrast, the electron appears to be elementary in our current theory. It does not seem to contain smaller parts. It can exist by itself. It does not feel the strong interaction. Comparing the electron and the quark is useful because both are basic matter particles, but their lives in the universe are very different. The electron has the freedom to roam. The quark does not. The electron can show up alone in a detector. The quark shows up only as part of a bound arrangement. There is also the matter of spin, another physical property that particles carry. Spin is one of those names in physics that sounds more ordinary than it is. It does not mean a quark is literally spinning like a tiny top. Instead, it is a built-in quantum property that affects how the particle behaves. Quarks have spin 1/2, which places them in the same broad category as electrons and other fermions. This matters for the structure of matter and for the rules about how particles can occupy states. Again, the details can become technical very quickly, but the key idea is that quarks are defined by a precise set of measurable properties. They're not vague little blobs. They are specific physical entities with exact roles in the theory. Perhaps the strangest thing about asking what a quark really is that the answer is partly about what it can do and partly about what it is not allowed to do. Most objects are introduced by listing their properties. A quark almost demands an extra line. It cannot exist in isolation. That fact is so central that leaving it out would give a false impression. Imagine explaining what a fish is without mentioning water. You could say it has fins, scales, a backbone, gills, and a certain body plan. And all of that would be true, but something essential would still be missing. A quark, without confinement, is a similarly incomplete idea. A quark is a matter particle defined in part by the force that binds it to other quarks so strongly that it never appears alone in ordinary conditions. That makes the quark less like a tiny bead and more like a member of a system whose identity is inseparable from interaction. This may feel slightly unsatisfying at first because our instincts prefer self-contained objects. We want the smallest things to be the most independent things. Yet physics does not always reward that instinct. Sometimes the deepest ingredients are the ones most tightly bound into relationships. Nature, in this case, does not hand us neat little independent pieces. It hands us basic entities whose existence is perfectly real, but whose separation is forbidden by the rules of the strong interaction. There is a lesson in that for how modern physics works. To understand matter at its deepest known levels, we have to stop demanding a picture that looks like the ordinary world. We have to accept that the universe is not made of tiny familiar objects. It is made of quantum entities with exact properties, and those entities combine, interact, and in some cases remain permanently confined. That is not less real than the world of stones and cups and chairs. It is simply more fundamental and less intuitive. And now, having said all of that, we are in a much better position to handle a detail that textbooks often introduce very early, but which makes more sense once the basic idea is steady in the mind. Quarks do not all come in one kind. There are several varieties, each with its own role and properties. Some are part of ordinary matter all around us, and some mostly appear in more extreme situations for very short times. Their names are memorable, mildly ridiculous, and completely standard in physics, which is one of the many reasons this subject remains impossible to discuss with a fully straight face for too long. So the natural thing from here is to look at those different kinds one by one, beginning with the most familiar pair and then moving outward into the rest. The first pair to meet are the ones that quietly run ordinary matter. If you stripped away all the complexity of daily life and asked which quarks are doing most of the visible work around you, the answer would be up and down. They are the familiar labourers of the subatomic world, the ones that build protons and neutrons, and through them build the nuclei of ordinary atoms. If quarks had a social hierarchy, which thankfully they do not because particle physics is already confusing enough without imagined office politics, up and down would be the ones handling the basic infrastructure, while the others drift in for more specialised and short-lived appearances. The name flavour is one of those pieces of physics vocabulary that sounds either charming or mildly unserious depending on your mood. It does not mean taste, of course. No one is seasoning a proton, it simply means type. There are 6 flavours of quark, and each flavour is a distinct kind of quark with its own mass and its own role in particle interactions. They all share the basic quark features. They all feel the strong interaction. They all carry colour charge. They all have spin 1/2, but they are not identical. They come in different versions, and those differences matter. The 6 flavours are called up, down, strange, charm, bottom and top. This list has a certain reputation among students because it sounds as though a serious branch of physics briefly passed through a stage of being named by a group of highly intelligent people trying not to laugh. And that is not entirely unfair. Particle physics contains some wonderfully formal mathematics attached to names that sound as though they were chosen during a long afternoon with too much coffee and a suspicious amount of confidence. Still, the names stuck, and now they are standard. Up and down come first because they are the lightest and the most important for ordinary matter. A proton is made from 2 up quarks and 1 down quark. A neutron is made from 2 down quarks and 1 up quark. That simple rearrangement changes the electric charge and changes the identity of the particle. It is one of the clearest examples of how quark content shapes the world. The proton is positively charged because the charges of its quarks add up to a full positive unit. The neutron is electrically neutral because its quark charges cancel in the right way. Once you see that, the names proton and neutron stop feeling like irreducible labels and start feeling like outcomes of a deeper recipe. This is one of the first great satisfactions in the quark model. The old particles of nuclear physics do not disappear. They become understandable in a new way. The proton is not just a positively charged particle because that is what nature declared in passing. It is positively charged because of the quarks inside it. The neutron is not neutral by some mysterious gift. It is neutral because of its internal quark arrangement. The deeper layer does not erase the old facts, it explains them. Up quarks carry an electric charge of 2/3 of the proton charge, and down quarks carry -1/3. That may sound unusual at first, but the combinations work beautifully. 2 ups and 1 down give a total of 1 positive unit. 2 downs and 1 up give 0. It is neat, and perhaps a little smug in how neatly it works. The universe often has that quality. It can behave in the strangest imaginable way and still arrange the details with irritating precision. Because up and down quarks are light, they dominate the stable matter around us. In this context, light means low in mass compared with the other quarks. Not that they glow or float around like cheerful dust motes. They are simply the least massive flavours, and that matters because heavy particles tend to decay into lighter ones when possible. The world settles downward. Stability usually lives among the lighter ingredients. That is why the atoms in your body, the air around you, the soil outside, and the stars that forged many of those atoms are all tied to up and down quarks. Ordinary matter is ordinary because these are the quarks that ordinary conditions favour. Then we come to strange, which is a lovely name for a particle, because it manages to sound descriptive and theatrical at the same time. Strange quarks were introduced to help explain particles that behaved oddly in experiments. Certain particles were being produced through strong interactions, which are fast, but then they decayed more slowly in ways that suggested another conserved property was involved. The behaviour seemed, quite literally, strange, so the name stuck. In one sense, it is a historical label left behind by confusion, which is very human. We find something unexpected, name it after the fact that it annoyed us, and then spend decades treating the name as perfectly normal. A strange quark is heavier than an up or down quark, but much lighter than the heaviest members of the family. It can appear inside particles called strange hadrons, such as kaons and hyperons. These are not the particles that make up stable everyday matter, but they are real and important in high-energy physics and in the history of particle theory. Strange particles helped reveal that the subatomic world was richer than the proton-neutron-electron picture first suggested. They were part of the reason physicists began suspecting that a deeper organising scheme was needed. In that sense, strange quarks help pry open the door to the quark model itself. What makes the strange quark especially useful in the story is that it shows how the universe can contain ingredients that are not part of ordinary stable matter, yet still matter profoundly for understanding the rules. Not everything fundamental has to sit quietly inside a table or a tree. Some ingredients only show up in energetic processes in short-lived particles, or in environments more extreme than everyday life. Physics does not grant importance only to what survives long enough to be built into furniture. Next comes charm, and this one enters the story with a little more confidence because it was proposed partly to bring order to the theory itself. Charm helped complete a pattern. It was not merely another oddity found in the data. It was also a way to make the mathematical structure cleaner and more consistent. Later, charm was discovered experimentally, which was a major success for the Quark model. It is always a good day in physics when the thing your equations quietly insist must exist eventually turns up in the laboratory. It is one of the few times theoretical pride and experimental patience get to shake hands. Charm quarks are heavier than strange quarks. They appear in particles such as charmed mesons and charmed baryons. These are not part of the durable matter of daily life either. They are produced in high-energy collisions and then decay. But again, their importance is not in everyday visibility. Their importance lies in how they confirm the structure of the theory. The family of quarks is not a random assortment. It comes in an ordered pattern, and charm is part of that order. In fact, the 6 quarks are often grouped into 3 pairs, sometimes called generations. The first generation contains up and down. The second contains charm and strange. The third contains top and bottom. Within each pair, one quark has a charge of 2/3 and the other has a charge of -1/3. This pattern is one of the clues that the particle world is structured rather than accidental. The generations differ mainly in mass. The higher generations are heavier and less stable. They tend to decay into lighter particles rather than hang around. This is why the first generation rules ordinary matter. Stability once again lives near the lightest option. Now, one curious thing about this generational structure is that the universe did not really need to be so generous. It could in principle have been built only from the first generation, and still given us ordinary atoms, chemistry, stars and people, sitting under blankets listening to physics at unwise hours. Yet it contains the heavier generations too. Why? That remains one of the deeper open questions. We know they exist. We know how they behave. We know how to produce them and detect their signatures. But why the particle family has exactly this layered structure is not something the standard model explains. It describes the pattern very well. It does not tell us why the pattern had to be that way in the first place. From charm we move to bottom, which was once also called beauty, because evidently somebody in particle physics looked at an extremely heavy quark and thought, yes, that one needs a stage name. Bottom is the more standard modern term, and probably the safer one if you're trying to sound calm and scholarly. Bottom quarks are much heavier than charm and strange. They appear in particles such as B mesons and bottom baryons, which are central to important experimental studies of particle decays and matter-antimatter asymmetry. These systems have taught physicists a great deal about how quarks transform from one flavour to another through the weak interaction. That last point is crucial. Although quarks are defined by flavour, flavour is not always permanent. Under the weak interaction, one flavour can change into another. This is how many particle decays happen. A down quark can change into an up quark in beta decay, for example, which allows a neutron to turn into a proton while also producing an electron and an antineutrino. This means flavour is not just a label pinned on forever. It is a real physical property, but one that can change under the right interaction. The strong interaction keeps quarks tightly bound, but the weak interaction allows flavour changes and therefore allows unstable particles to decay into more stable ones. Bottom quarks are especially useful in experiments because their decays can be measured carefully, and those decays probe the subtle workings of the weak force and the mixing between quark flavours. There is an entire piece of particle physics devoted to watching heavy quarks decay and asking whether matter and antimatter behave in exactly symmetric ways. The answer is no, not quite, and that slight imbalance may connect to one of the grandest questions of all, namely why the universe contains so much matter and so little antimatter left over. So even the heavier, rarer quarks that never become part of stable daily matter still participate in some of the most important scientific questions we can ask. And then we arrive at Top, the giant of the family. The top quark is by far the heaviest of the 6. In fact, it is so heavy that it behaves unlike the others in a remarkable way. Most quarks, once produced, very quickly become part of bound states, hadrons, because the strong interaction confines them. The top quark is different. It decays so rapidly that it does not usually have time to form ordinary hadrons before it is gone. This makes it unusual among quarks, almost a special case written in the margin of the family. It is still a quark, it still carries the defining quark properties, but it vanishes with extraordinary speed. That makes the top quark interesting for 2 reasons. First, it tells us just how broad the quark family really is in terms of mass. The leap from up and down to top is enormous. These are not 6 nearly identical ingredients with slightly different labels. They span a huge range. Second, the top quark gives physicists a way to study a quark in a cleaner state than usual, not because it exists freely in the ordinary sense, but because it decays before the messy business of hadron formation fully takes over. In that narrow technical sense, Top is an odd gift from the universe. It is difficult, fleeting, and extremely informative. Once you have all 6 flavors in view, a useful question naturally appears. Why only up and down in ordinary matter? Why are the others absent from the stable world around us? The answer is mostly mass and decay. Heavier quarks do not hang around because there are lighter possibilities available. Given time, unstable systems decay downward into more stable combinations built from the lightest quarks. Strange particles live longer than many other unstable particles, but not indefinitely. Charmed, bottom, and top-containing particles decay faster. The result is that the visible, durable universe settles into the first generation. It is not that the other quarks are less real. It is that the world does not freeze at high energy. It cools, relaxes, and keeps what lasts. There is also a more subtle point here. Even though protons and neutrons are described by up and down valence quarks, their interiors are not made only of those 3 quarks sitting in quiet dignity. As we have already touched on, the strong interaction fills the proton with gluons and with fleeting quark antiquark pairs. In that dynamic sense, the interior of a proton can briefly contain more complexity than the simple 3 quark picture suggests. But the defining flavor content, the identity given skeleton of the proton and neutron, is still built from up and down. Another question people often ask is whether the flavors are just names for mass differences, or whether they are truly distinct. The answer is that they are truly distinct. Mass is one difference, but not the only one. Their roles in weak interactions, their place in the generation structure, and the way they contribute to the identities of composite particles all matter. Flavor is a genuine physical classification, not just a convenient nickname for lighter and heavier versions of the same thing. By now, the list itself may feel less arbitrary. Up and down are the stable foundation. Strange and charm belong to the next heavier generation. Bottom and top form the heaviest pair. Each pair repeats the pattern of one quark with 2/3 charge and one with -1/3 charge. The family is orderly, even if the names sound like they were chosen by a committee that briefly escaped supervision. Yet for all their differences, the 6 flavors share the same deep predicament. None of them, aside from the special fleeting case of the top before it decays, gets to live alone in the world we observe. Whether light or heavy, common or rare, they are subject to confinement. The strong interaction does not care that one is called strange and another up. It binds them all. The flavors change what particles can be built, how those particles behave, how heavy they are, and how they decay. But the basic rule remains. Quarks appear in combinations. And this brings us naturally to one of the most misleading names in all of physics. Because if flavor sounds pleasantly culinary, the next idea sounds as though someone confused a particle accelerator with an art supply cabinet. To understand why quarks combine the way they do, and why only certain combinations are allowed, we need to talk about color charge. It has nothing to do with visible colour, which is fortunate because the inside of a proton is already busy enough without trying to repaint it. But despite the silly-sounding name, colour charge is one of the central ideas in the whole subject, because it tells us what kind of force quarks feel and why that force behaves so very differently from the ones we know best. The word colour charge has probably caused more completely reasonable confusion than almost any other phrase in particle physics. If you hear it for the first time, you can be forgiven for imagining that someone has discovered tiny patches of red and blue inside matter, or that the proton has a hidden interior decorating scheme. It does not. Nothing inside a proton is literally coloured in the visual sense. There are no little painted quarks, no microscopic rainbows, and no subatomic art studio quietly operating at the centre of the atom. The name is borrowed language, and like a great deal of borrowed language in physics, it is both helpful and slightly annoying. Still, once the irritation settles, colour charge turns out to be one of the most important ideas in the whole story. In fact, if you want to understand what a quark really is, why quarks combine the way they do, and why they never appear alone, then colour charge is not an optional detail. It is central. Without it, quarks would just be oddly named particles with unusual electric charges. With it, they become part of a very specific and very powerful theory of how matter is held together at the deepest known level. The first thing to keep clear is that colour charge is not the same as electric charge. Quarks have electric charge, yes, but they also have colour charge, and these are different properties. Electric charge tells you how a particle responds to the electromagnetic force. Colour charge tells you how it responds to the strong interaction. The strong interaction is the force that binds quarks together into larger particles such as protons and neutrons. So when physicists say that quarks carry colour, they mean quarks possess the kind of charge that the strong force acts on. That raises an obvious question: why call it colour at all? The short answer is that the theory needed labels, and 3 labels were especially useful. Physicists chose names corresponding loosely to 3 colours: red, green, and blue. Again, not because quarks are visually red, green, or blue, but because using 3 distinct labels helped keep track of how the theory worked. In this sense, the name is a bookkeeping device with a very grand career. It sounds decorative, but it is really structural, and it had to be structural because something important needed explaining. Quarks were being proposed as the constituents of hadrons, including protons and neutrons. But there was a puzzle in how some of these particles were built. For example, certain particles seem to require multiple quarks of the same flavour and the same spin arrangement. According to the usual rules for fermions, which are the rules quarks obey, that should not have been allowed if those quarks were identical in every relevant way. Something had to distinguish them. Colour charge provided that distinction. It allowed quarks of the same flavour to exist together in a way that preserved the rules of quantum mechanics. So colour charge was not just a cute naming trick. It solved a real physical problem. It gave quarks an additional property, one that let the theory make sense of observed particles while also defining how the strong interaction works. That is the moment where the misleading name stops being a nuisance and starts earning its place. Now, when 3 quarks come together to form a proton or neutron, they do not just gather randomly. Their colour charges must combine in a very specific way. The allowed combinations are colour neutral overall. That phrase matters. A particle we can observe on its own in ordinary conditions must not carry a net colour charge. In a baryon, which is a particle made of 3 quarks such as a proton or neutron, the 3 different colours combine to produce a colourless state. In a meson, which is made of a quark and an antiquark, a colour and the matching anticolour combine to produce another colourless state. Colourless here does not mean transparent or pale or visually blank. It means neutral with respect to the strong interaction in the overall observable sense. This is already very revealing. It means quarks do not just gather because they happen to be nearby. They form combinations that satisfy the deeper rules of colour neutrality. Observable particles are not simply bundles of quarks. They are bundles arranged in ways that hide the net color from the outside world. That is one reason single quarks do not show up in isolation. A lone quark would carry color charge by itself. Nature, at least under ordinary conditions, does not offer us such isolated colored objects. If this seems similar to electric neutrality, that is a useful comparison up to a point. An atom can be electrically neutral when positive and negative charges balance. In a rough and limited sense, hadrons are color neutral when their color charges combine properly. But the analogy only goes so far because the strong interaction behaves very differently from electromagnetism, and this is where color charge becomes much more than a simple extra label. In electromagnetism, the force carrier is the photon. Photons do not carry electric charge. That means the electromagnetic field behaves in one particular way. The force weakens with distance in the familiar manner, and the carriers do not directly interact with one another through electric charge. The strong interaction is different. Its force carriers are gluons, and gluons themselves carry color charge. That changes the whole personality of the force. This is one of the most important differences in particle physics. The messenger of the strong interaction is not neutral with respect to the charge it carries. It participates in the very thing it transmits. That means the field of the strong interaction can interact with itself. This makes the theory richer, more difficult, and more remarkable. It also helps explain why the strong force behaves in ways that seem so unlike everyday intuition. Inside a proton, quarks are constantly exchanging gluons. That exchange is what binds them together. But unlike the clean cartoon picture where three objects sit politely in a triangle and pass little packets back and forth, the reality is much more active. The color charges of the quarks are continuously being exchanged through gluons. A quark that was red a moment ago can emit or absorb a gluon and become green, while another quark changes correspondingly. The important thing is not that each quark keeps one permanent visual label like a well-organized office badge. The important thing is that the whole system maintains the correct overall color-neutral state as these interactions continue. This can be difficult to picture because the mind wants stable labels. We prefer to imagine that each quark simply has its assigned color and keeps it, but the strong interaction does not sit still for our convenience. The colors are part of a dynamic quantum process. What remains stable is not the permanent color of each individual quark, but the lawful structure of the whole system. There is also a deeper point here about why color charge got its name in the first place. Using three colors was useful because three combine into a neutral whole, in an analogy to ordinary color mixing where red, green and blue light combine to make white. That analogy is only partial and must not be taken too literally, but it provided a memorable framework. In the theory, the requirement is not visual whiteness, but color neutrality. Even so, the naming made the abstract rule easier to talk about. It is one of those rare cases where physics borrowed a familiar word and actually did gain something from it, even if generations of students have spent their first few minutes with the subject wondering whether protons are secretly festive. So far, we have focused on ordinary hadrons, the observable particles built from quarks. But the true force of color charge becomes clearer when you ask what happens if you try to separate quarks. This is where the strong interaction departs most sharply from common expectation. If you pull electrically charged particles apart, the electric force between them weakens with distance. But when you try to separate quarks, the strong interaction does not simply fade away. The color field between them behaves more like a stretched connection that resists more strongly as the separation grows. It is tempting to use the word string here, and physicists often do in rough explanations, because the color field between quarks can act somewhat like an extended tube of energy. As the quarks move apart, energy builds in that field. You might expect that with enough effort you could eventually overcome the attraction and isolate a single quark. But the universe has a different plan. Before you get a lone quark, the energy in the stretched field becomes large enough to create new quark-antiquark pairs. Instead of one isolated quark, you end up with new color-neutral particles. The system rearranges itself. You do not get freedom, you get more hadrons. This behaviour is called confinement, and colour charge is the reason confinement happens. It is not just that quarks happen to like company. It is not that we have not built a sufficiently determined machine. It is that the strong interaction defined by colour charge binds quarks in such a way that isolated colour-charged objects do not emerge under ordinary conditions. That is an extraordinary statement. A basic constituent of matter exists, but only in combinations that hide its defining strong charge from direct isolation. This is also why the name gluon is rather good, even if it sounds like something sold in a craft store with stern warnings on the label. Gluons really do glue quarks together. They are the carriers of the strong interaction, and because they themselves carry colour charge, the glue is not passive. It has structure, tension, and self-interaction. That is a very different kind of glue from anything in ordinary life. It is less sticky paste and more a deeply active binding system governed by quantum field theory. Once you appreciate this, a proton stops looking like a quiet object and starts looking like a dense, restless colour-neutral arrangement of quarks and gluons. The three valence quarks set the basic identity, yes, but the gluons are not secondary decorations. They are essential, they carry momentum, they contribute energy, they help determine the mass and behaviour of the proton. In that sense, colour charge is not just a hidden tag attached to quarks, it shapes the very existence of the visible matter around us. And it does so in another interesting way. At very short distances, quarks behave almost as if they are less tightly bound. This feature is called asymptotic freedom. The name sounds a little dramatic, but the idea is important. When quarks are extremely close together, the effective strength of the strong interaction becomes weaker. When they are pulled farther apart, it becomes stronger. That is almost the opposite of what intuition trained on gravity or electricity expects. Close means more freedom. Farther apart means stronger confinement. Nature has turned the usual social rules upside down. This feature helped establish the modern theory of the strong interaction as a full quantum field theory. It explained why high-energy scattering experiments could sometimes make quarks inside hadrons look almost like free constituents during a very brief interaction. They were not truly free in the sense of being isolated and captured afterward, but at very short distances and high energies their behaviour reflected this reduced effective coupling. That was a major success for the theory. It connected the deep mathematics of colour charge to real experimental observations. The theory built around colour charge is called quantum chromodynamics. The name sounds severe, but it simply means the quantum theory of colour. It is the part of the standard model that describes quarks and gluons and the strong interaction between them. Quantum chromodynamics is one of the best tested theories in all of science, though it is not always the easiest to solve in practice, especially at the low energy scales relevant for bound hadrons. The equations are powerful, but the actual behaviour of strongly interacting systems can be very hard to calculate exactly. Nature is lawful here, but not especially cooperative. That difficulty itself tells you something important. Colour charge is not a decorative patch on top of particle physics. It is one of the reasons the subject is both deep and hard. The strong interaction is not messy because physicists forgot to simplify it. It is genuinely rich. The carriers interact with each other. The force changes with scale. Bound states dominate the world we actually observe. All of that comes from the structure introduced by colour charge. A useful way to summarise this is to say that electric charge tells you how a particle responds to light and magnetism, while colour charge tells you how a quark participates in the intense subatomic binding that builds hadrons. But the summary should not hide the strangeness. Colour charge is not just another label in the same style as electric charge. It belongs to a force with a very different personality. That is why a single electron can drift through space, while a single quark cannot. The charges are different, the carriers are different, and the whole architecture of the interaction is different. This also helps answer a question that often lingers in the background. Why do protons and neutrons hold together internally at all? After all, quarks inside a proton are not electrically arranged in some perfectly calm way. There is motion, there is energy, there is exchange. The answer is that the strong interaction associated with colour charge dominates at that scale. It is immensely powerful over short distances. It binds quarks into hadrons, and then a related residual effect of that same interaction helps bind protons and neutrons together inside atomic nuclei. So even the solidity of the atom rests, at a deeper level, on colour charge doing its work among quarks. The misleading part of the name never really goes away. Colour still sounds like something from the visible world, and every student has to unlearn that first impression. But once that is done, the idea becomes crisp. Quarks carry colour charge, gluons transmit the strong interaction, and carry colour charge too. Observable particles must be colour neutral overall. The field between quarks resists separation in a way that leads to confinement. And this is why quarks can help build nearly everything around us while never stepping out alone. At that point, the next step follows almost automatically, because once colour charge is on the table, gluons stop being a side note and become the main actors in the binding itself. They are the carriers of the force that never simply lets go. And to understand why a quark cannot exist alone, we now have to look more closely at what those gluons are doing inside the particles that hold the visible universe together. Once colour charge is in place, the next thing that has to come into focus is the gluon, because colour charge on its own is only a label until there is something that responds to it and carries its influence from one quark to another. Gluons are the particles that do that work. They are the carriers of the strong interaction, the force that binds quarks together inside protons, neutrons, and many other particles. If quarks are the matter ingredients in this part of the story, gluons are the reason those ingredients do not drift apart and go their separate ways. The name gluon is one of the few cases in physics where the informal-sounding word is almost suspiciously appropriate. Gluons do glue quarks together, but that phrase can mislead if it makes you think of ordinary glue, something passive, sticky, and more or less content to sit there between two surfaces. The binding created by gluons is nothing like a layer of paste between bits of wood. It is an active quantum interaction. It is dynamic, restless, and inseparable from the particles involved. The gluons are not background support staff quietly maintaining the structure, while the quarks get all the attention. They are central to what the structure is. A good way to begin is by comparing gluons with photons, because photons are the better-known carriers of a force. Photons carry the electromagnetic interaction. They are responsible for the electric force and for light. If two electrically charged particles interact, photons are the carriers in the quantum description. That already gives us a useful framework. Nature often describes forces through particles that mediate interactions. So far, so familiar. But the similarity only lasts for a moment, because gluons behave in a way that makes the strong interaction fundamentally different from electromagnetism. The crucial difference is that photons do not carry electric charge. Gluons do carry colour charge. That single fact changes almost everything. A photon can mediate the electric force between charged particles, but it does not itself participate in electric charge as a source in the same way. Gluons are not so restrained. Because they carry colour charge, they can interact with quarks and with each other. This means the force field of the strong interaction is not a simple, quiet channel between separate sources. It has its own internal complexity. The field can bend back on itself, influence itself, and produce behaviour that is much richer and much less intuitive than the electromagnetic case. That is why the strong interaction behaves with such a different personality. If you pull two electric charges apart, the force between them weakens with distance in the familiar way. It becomes harder for them to strongly influence each other when they are far apart. But the strong interaction between quarks does not fade in that same simple manner. In fact, once quarks are no longer extremely close together, the field between them acts in a way that makes separation increasingly difficult. The interaction does not politely weaken and let go. It resists, it tightens, it stores energy as the quarks are pulled apart. This is why the force is often described as the one that never lets go. Now that phrase should not be taken to mean that quarks are frozen in place like insects in amber. The inside of a proton is not static, it is active beyond anything the word glued might suggest. Quarks move, gluons are exchanged continuously, energy flows through the system. Additional quark-antiquark pairs can appear briefly as part of the quantum structure. The point is not that the components are motionless. The point is that the binding remains. No matter how active the interior becomes, the quarks do not simply escape one by one into independent existence. This is where the image of a proton as three neat little beads becomes especially unhelpful. A proton is better thought of as a tightly bound quantum state made of quarks and gluons, with constant interaction at its core. The gluons are not occasional messengers dropping by to keep the peace. They are continuously exchanged, and in doing so they change the colour charges of the quarks, while preserving the overall colour-neutral state of the system. A quark that one moment is in one colour state can emit or absorb a gluon and shift to another, while the rest of the system adjusts accordingly. The internal bookkeeping never stops. If that sounds busy, it is because it is busy. There is no still life inside a proton. There is only lawful motion. It is also important to notice that gluons contribute to the proton in a more substantial way than people often expect. In a first simplified telling, the proton is made of 3 quarks. That is useful as a first sentence, but only as a first sentence. The full picture includes the gluon field and the sea of temporary quark-antiquark activity that this field helps sustain. Much of the energy of the proton comes from this internal dynamical structure. In fact, most of the proton mass is not simply the sum of the bare masses of its valence quarks. The energy carried by the gluons and by the motion of the quarks contributes enormously. This is one of those facts that sounds technical until it settles in, and then it quietly changes the way you think about matter. The weight of ordinary matter is deeply tied to a storm of interaction inside particles that seem, from a distance, wonderfully solid and calm. So gluons are not extras. They are part of the reason matter has the character it does. There is also a useful question that comes up here. If gluons are the carriers of the strong interaction, why do we not talk about them in everyday matter, the way we talk about electrons? Why do they not seem to appear as separate travelling objects in ordinary life? Part of the answer is that gluons themselves are subject to the rules of the strong interaction, because they carry colour charge. They are not free of the system they mediate. This means that just like quarks, they do not roam around independently under ordinary conditions. They belong inside colour-neutral combinations. In that sense, the strong interaction keeps both its matter particles and its force carriers on a short leash. This makes the strong interaction rather unusual among the fundamental forces. It is not merely powerful, it is self-contained in a deep way. The ingredients it acts on, and the particles that carry it, are both woven into a structure that hides the underlying colour charge from direct isolation. That is why the visible world is made of hadrons and nuclei, rather than loose quarks and free gluons drifting past your tea. At very short distances, however, the story changes slightly. Quarks that are extremely close together behave as though the strong interaction becomes weaker. This is the feature called asymptotic freedom. The name can sound grand, and possibly a little over-enthusiastic, but the idea is simple enough. When quarks are almost on top of each other at tiny scales, the effective binding becomes less severe. They move in a way that looks closer to free during very high-energy interactions. This helped explain why scattering experiments could reveal point-like constituents inside protons. During those brief violent encounters, quarks behaved almost as though they were not strongly bound, but that temporary near freedom should not be mistaken for actual liberation. As soon as you move away from those extremely short distance conditions, the full confining character of the force returns. This gives the strong interaction an almost inverted logic compared with our usual instincts. Close together, the quarks act less tightly trapped. Pull them apart and the force grows more punishing. The farther toward independence you push them, the harder the universe pushes back. It is a remarkable rule. One might have guessed the opposite. One might have assumed that strong binding would be strongest at very short distance and weaker farther out. Nature chose a subtler arrangement. A helpful picture, though only a picture, is to imagine the field between quarks not spreading out gently in all directions the way the electric field does, but narrowing into a kind of tube of energy between them. As the quarks separate, that tube stretches, and the energy stored in it increases. The exact mathematics is more sophisticated than any image like this can capture, but the picture helps explain why separation does not become easier with distance. You're not weakening the connection, you're loading it with more energy, and at some point that energy becomes enough to produce new quark-antiquark pairs from the vacuum. So instead of isolating one quark, you create new bound particles. The system breaks not into freedom, but into fresh combinations. This is one of the most striking consequences of gluon-mediated binding. The attempt to pull matter apart at this level does not reveal isolated pieces in the usual sense. It reorganizes the pieces into new composite particles. It is as though the force refuses to permit the question in the form you asked it. You say, "Show me one quark by itself," and the universe replies no, but here are two new hadrons for your trouble. That behavior is why so much of particle physics involves jets rather than lonely quarks. In high-energy collisions, quarks can be struck hard and sent flying away from one another, but detectors do not then record little free quarks arriving on their own. Instead, the energy reorganizes through hadronization, producing sprays of ordinary particles. Those jets are one of the experimental signatures that quarks and gluons are there. We infer the underlying quark and gluon activity from the patterns of the particles that emerge. The basic constituents show themselves through consequences rather than by stepping politely into view as isolated specimens. This is not a weakness of the theory. It is one of its strongest features. The theory does not merely say that quarks exist and then shrug when asked why they are never seen alone. It explains why the force carried by gluons makes that impossible under ordinary conditions. The same idea that binds protons and neutrons internally also tells us why the constituents do not walk out of the structure one at a time. The formal theory behind all this is quantum chromodynamics, the quantum theory of quarks and gluons. It is one of the pillars of the Standard Model and one of the most successful theories ever built. Yet it is also a theory with a rather split personality when it comes to practical understanding. At very high energies and short distances, it becomes mathematically more manageable because the interaction weakens. At lower energies, where bound states dominate, calculations become much harder. This is one reason the proton is so much more than a simple object. The underlying rules are clear, but the full behavior of strongly interacting matter can be extraordinarily difficult to work out in detail. Physicists often turn to large-scale numerical methods to study this low-energy regime. They simulate the theory on a discrete grid and compute the behavior of quarks and gluons in a controlled way. This has been an important route to understanding hadron masses and other properties. It is a reminder that even when the theory is well established, nature can still make the practical consequences very hard to extract. The world is under no obligation to be easy to calculate just because it is lawful. Still, the broad physical picture is clear. Gluons bind quarks because quarks carry color charge. Gluons themselves carry color charge, which makes the interaction self-coupled and rich. At very short distances, the binding weakens, allowing quarks to behave almost freely in certain high-energy situations. At larger separations, the binding strengthens, preventing isolation. The result is confinement, and confinement is why hadrons exist as the observable units of strongly interacting matter. There is also something worth pausing over in the word force itself. In ordinary life, force suggests a push or a pull between objects that already exist independently. You push a door, gravity pulls a book downward, magnets attract a note to the refrigerator. Those are all cases where the objects themselves make sense apart from the force. With gluons and quarks, the situation is deeper. The strong interaction does not merely act on pre-existing little objects in a casual external way. It helps define what kinds of objects can stably exist at all. Because of gluon-mediated confinement, isolated quarks are not part of ordinary observable reality. So the force is not just a relationship between things. It shapes which things are allowed to appear separately. That makes gluons unusually important philosophically as well as physically. They remind us that at the deepest levels, the universe may not be built from tiny independent items that then happen to interact. Instead, the interaction can be part of what gives the items their effective existence in the world we can observe. A quark inside a hadron is real, measurable, and indispensable, but the same theory that gives it meaning also forbids its separate appearance. Gluons sit right at the centre of that fact, and they do one more thing that deserves attention. Because they carry so much of the internal energy of hadrons, gluons help explain why the proton is heavier than a simple, naive sum of quark masses would suggest. This means that the apparent solidity and mass of ordinary matter rests to a remarkable degree on the energy of the gluon field and the motion it sustains. The chair, the wall, the hand resting beside you, all of these owe much of their mass to a strong force process unfolding continually inside protons and neutrons. That is a quietly astonishing thought. The ordinary world feels calm, but deep inside it is held together by a force that never relaxes into passivity. You can also see now why gluons do not receive as much popular attention as they deserve. Quarks are easier to make into headline material. They sound like the ingredients. They have memorable flavour names. They fit the story of matter being made of smaller pieces. Gluons are less glamorous at first glance. They sound like support. But without gluons, quarks would not form protons or neutrons. Without gluons, there would be no stable hadrons. Without gluons, the structure of ordinary matter would collapse before it ever began. If quarks are the cast, gluons are the reason the stage exists, and the reason everyone remains in the same play. By this point, the phrase, the force that never lets go, should feel less like a dramatic flourish, and more like a careful description. The gluon-mediated, strong interaction does not permit quarks to separate cleanly. It binds them into color-neutral states. It stores energy when separation is attempted. It replaces isolation with rearrangement. It makes the inside of a proton a dynamic system rather than a tiny container. And it contributes directly to the mass and character of the visible matter that fills the universe. So when we next ask the question that has been hovering over the whole story from the beginning, why a quark cannot exist alone, we're no longer asking it in a vague or mysterious way. We already know the heart of the answer. We know that quarks carry color charge. We know that gluons carry that charge too and create a self-interacting field. We know that the force strengthens as separation grows, and that means the impossibility of a lonely quark is not a side note or an experimental inconvenience. It is written into the very structure of the strong interaction itself. By now the question has narrowed into its most interesting form, not just what a quark is, and not just what color charge means, but why a quark cannot exist alone. This is the point where the story stops sounding merely unusual and starts sounding almost unreasonable. A quark is fundamental. It is one of the deepest known constituents of matter. It has definite properties. It helps build protons and neutrons and many other particles, and yet it never shows up by itself in the ordinary observable world. That combination of facts is so strange that it deserves to be handled slowly, because if you rush it, it can sound like science is trying to have things both ways. It is real, but never alone. It is basic, but never solitary. It is everywhere inside matter, yet nowhere as an isolated object. So why? The short answer is confinement. The longer answer is that the strong interaction, the force carried by gluons and governed by color charge, does not let quarks separate in the way our everyday intuition expects. If you try to pull a quark away from the other quarks it is bound to, you do not gradually weaken the connection until the quark comes free. You do the opposite. You increase the energy stored in the field between them. The harder you try to isolate the quark, the more energy piles into the system, until the system responds by creating new particles. What you get in the end is not one lonely quark, but fresh combinations of quarks and antiquarks, arranged once again into colour-neutral particles. The universe does not give you freedom at the end of the process, it gives you rearrangement. That is the essential idea, but it helps to feel why it is so different from the forces we know best. In ordinary life, separation tends to make binding weaker. If two magnets are close, their pull may be noticeable. Move them farther apart and the effect drops. Gravity behaves that way too. The farther away two masses are, the weaker their attraction. Even something like a stretched rubber band, though it resists being pulled, is still an ordinary object with an obvious limit. If you pull hard enough, it snaps, and the two ends fly apart. Our instincts are trained by systems like that. We expect enough effort to produce separation. Quarks do not cooperate with that expectation. The force between them behaves in a way that is more like a connection, whose stored energy keeps growing as you pull. A loose analogy is a tensioned cord that does not simply weaken or break into two clean, free pieces. Instead, when enough energy is stored, the cord uses that energy to make new endpoints. That is not exactly what happens in the mathematics, but it gets the spirit right. Pulling on the system does not uncover an isolated quark. It creates the conditions for new hadrons to form. This is why the phrase why a quark cannot exist alone is not really a question about our instruments being too weak or our experiments being too clumsy. It is not that quarks are merely hard to isolate in the practical sense, like trying to pick up smoke with chopsticks. It is that the theory of the strong interaction says isolated quarks are not available as stable observable objects under ordinary conditions. The very act of trying to separate them changes the system in a way that prevents the outcome you wanted. That is one of the most remarkable things in modern physics. Usually when we identify a constituent of some larger object, we imagine that constituent could in principle be extracted. If a molecule is made of atoms, the atoms can exist on their own. If a mineral contains certain elements, those elements can appear elsewhere independently. But quarks break that pattern. They are constituents without being independently available in the usual way. They are more like ingredients that only ever appear inside finished combinations. And the reason is not vague mystery. The reason is the specific behavior of the strong interaction. A useful way to think about this is to remember that quarks carry color charge, and observable particles must be color neutral overall. A lone quark would carry net color. A proton does not. A neutron does not. A meson does not. The particles we observe are all color neutral combinations. The universe appears to permit only those combinations as free hadronic states under normal conditions. This is not an added rule pasted awkwardly on top of the theory. It is what emerges from the dynamics of quantum chromodynamics, the theory of quarks and gluons. At extremely short distances, quarks behave almost as though they are less tightly bound. This is the feature called asymptotic freedom. It is one reason high-energy scattering experiments can reveal quark-like behavior inside protons. During a violent collision, on those tiny scales and for those brief intervals, the quarks act nearly free. That might sound like a loophole. It sounds as if perhaps freedom is possible after all, but the loophole closes quickly. The moment you try to turn that brief near freedom into actual separation over larger distances, the interaction strengthens again. The quark never arrives as an isolated object in a detector. Instead, the energy of the situation produces sprays of hadrons. The quark shows itself indirectly, through patterns in the aftermath. This is worth emphasizing because it explains a common confusion. People sometimes hear that quarks inside a proton can act almost free in certain experiments, and they imagine that physicists have nearly caught individual quarks, but not quite. That is not the right picture. The high-energy behaviour tells us quarks are there as constituents. It does not mean they're on the verge of becoming freely observable particles. The same theory that lets us probe them at short distances also tells us why the end state of the experiment is made of hadrons rather than lone quarks. The experimental evidence for this is overwhelming. In particle colliders, when protons are smashed together at high energies, the internal quarks and gluons participate in the collision. We do not see single quarks flying into the detector and stopping as tiny isolated units. What we see are jets, narrow sprays of ordinary particles emerging in directions that reflect the original quark and gluon activity. These jets are one of the signatures of the quark world. They are like footprints in snow. You do not see the traveller directly standing still for a portrait, but the pattern left behind tells you very clearly that someone passed through. Quarks are known from their consequences, and one of the clearest consequences is that attempted separation ends in hadron formation. Now, one might still ask whether perhaps somewhere in the universe, under exotic conditions, free quarks could exist. That is a more subtle question. In ordinary matter and ordinary experiments, confinement rules decisively. But in the extreme early universe, when temperatures were unimaginably high, quarks and gluons were not bound into hadrons in the way they are now. There were conditions in which matter existed as a quark-gluon plasma, a state where quarks and gluons moved in a deconfined medium. Even today, in very high-energy heavy ion collisions, physicists can briefly create matter that behaves somewhat like this plasma. But this does not mean isolated, permanently free quarks wandering around as stable objects. It means the confining structure of ordinary hadrons can melt under extreme conditions. That is a very important distinction. A deconfined medium is not the same thing as a single quark living independently in calm ordinary space. So when we say a quark cannot exist alone, what we mean is that under normal observable conditions, isolated quarks do not appear as free asymptotic states. That is the technical statement underneath the plain language. The strong interaction confines them into colour-neutral combinations. The only way around that is to create conditions so extreme that the very notion of separate hadrons temporarily dissolves into a dense plasma, and even then, once the system cools, confinement returns and hadrons form again. This is one reason quarks are such an important correction to our mental picture of matter. We are used to the idea that the deeper we go, the more we find independent pieces, but the quark teaches a different lesson. At the deepest known level of visible matter, the independent pieces are not simply available as separate objects. Instead, the rules of interaction determine what can stably exist as a distinct thing. The force is not an optional relationship between already free constituents. It is part of what decides whether those constituents ever show up on their own. There is something almost paradoxical about that. A quark is real, but not independently present. It contributes to the mass, charge, and structure of hadrons. It leaves its imprint in scattering experiments. It is required by the theory. Yet if you ask for one by itself, the universe refuses the request. This is not because the quark is vague or half-real. It is because the concept of a free isolated quark is not part of the ordinary physical world described by the theory. The theory gives us quarks, but it gives them to us in bound states. That makes quarks different from electrons in a very instructive way. Electrons are also fundamental matter particles. They also belong to the deepest known layer of the Standard Model. But electrons carry electric charge, not colour charge, and electromagnetism does not confine them. An electron can leave an atom and travel freely. That is why electricity works, why currents flow, why electrons can be emitted, accelerated, and detected as individual particles. Quarks cannot do that. They are confined by a force whose structure is far less forgiving. Comparing electrons and quarks helps show that the oddness is not in fundamental particles as such. It is in this particular force, and the kind of charge it acts on. Another useful comparison is with the nucleus itself. Protons and neutrons are bound together in nuclei by the residual strong interaction, but that binding can be overcome. Nuclear reactions can split nuclei. Individual protons and neutrons can certainly exist on their own outside a nucleus. So even there, the binding is not absolute confinement. A neutron outside a nucleus is unstable over time, but it still exists as a free particle for a while. A proton can exist freely for as long as we have ever observed. The quark is more deeply trapped than either. It is not just bound in the usual sense. It is confined in a way that prevents separate observation altogether. This is where the role of gluons becomes especially important. Because gluons carry color charge themselves, the strong interaction does not spread out in the simple way an electric field does. The field between quarks becomes concentrated, often described roughly as a flux tube of energy. As separation increases, so does the energy stored in that tube. It is this behavior that makes isolation fail. In effect, you do not run out of force as you pull. You accumulate energy until particle creation becomes favorable. The vacuum in quantum field theory is not empty in the ordinary everyday sense. With enough energy concentrated in the right way, new quark-antiquark pairs can be produced. Once that happens, the system reorganizes into color-neutral hadrons again. This means the attempt to isolate a quark changes the question from can I free this constituent to how will the system reassemble under increasing energy? And the answer is that it reassembles into hadrons. This process is called hadronization. It is one of the central reasons collider physics looks the way it does. Instead of catching free quarks, detectors record showers of mesons and baryons that preserve the information about the underlying event in a coded but measurable form. A nice side effect of this, if one can call it nice, is that quarks become known through patterns rather than through direct visual style intuition. Physics at its best often works this way. You do not always get to observe a thing in the simple manner the imagination prefers. Sometimes you learn it through structure, through repeated consequences, through the stubborn consistency of results across many different experiments. Quarks have earned their place by that standard many times over. Their confinement does not weaken their reality. It sharpens the lesson of what reality at small scales can look like. There is also a quiet philosophical change hidden here. In the ordinary world, being a thing often seems to mean being able to stand alone. A chair stands in a room, a stone sits on a path. A glass can be set on a table by itself. Independence feels like part of objecthood. Quarks challenge that intuition. They are things in physics, yet not things in the everyday isolated sense. Their identity is deeply tied to the combinations they inhabit. They are not illusions, and they are not merely placeholders. But they are not freestanding citizens of the visible world either. They exist within bound structures so deeply that trying to pull them out only creates new structures. This does not make the universe less understandable. It makes it more interesting and perhaps more honest. It reminds us that our common sense picture of an object is local and limited, shaped by the scale at which we live. At smaller scales, the world is not obligated to give us miniature versions of apples, marbles, and coins. It gives us quantum fields, confinement, emergent mass, and constituents that can only be known through relationship and interaction. That may feel unfamiliar, but unfamiliar is not the same as incoherent. In fact, once the idea settles, quark confinement is one of the most coherent features of the whole theory. And there is another consequence worth noticing. Because quarks cannot be isolated, much of what we call ordinary matter is more collective than it first appears. The proton is not merely a box containing 3 tiny particles. It is a bound state whose existence depends on continuous interaction. The neutron is the same kind of story. If quarks could exist freely, matter would look very different. The visible universe as we know it depends on confinement. The stability and character of atoms, nuclei, and everything built from them rests on this deep refusal of quarks to live alone. So the answer to the question is not that a quark lacks the courage to go out by itself, though one can imagine the poor thing standing at the threshold of the proton, looking at the vast universe outside and deciding the weather is not suitable. The real answer is more exact and more profound. A quark cannot exist alone because the strong interaction associated with colour charge confines it. Pulling it away from its partners strengthens the field rather than weakening it. The energy of that field grows until new quark-antiquark pairs are created. The outcome is always new colour-neutral combinations, not isolated colour-charged particles. Once that is understood, the proton itself begins to look different. It stops being a simple little object with three fixed contents and starts looking like a dynamic, crowded quantum system full of exchange, motion, and hidden activity. The three valence quarks are still central, but they are not the whole story. Around them is a sea of gluons and temporary pairs, all contributing to the particle we casually call a proton. And that is where the road leads next, because having understood why a quark cannot stand alone, the natural thing now is to look more carefully at the place where quarks do live, not as static residents, but as part of a surprisingly turbulent interior world. When most people first hear that protons are part of atoms and that atoms are the material basis of everything around us, it is very natural to imagine the proton as a tiny solid nugget. Small, dense, compact, and finished. Even after learning that the proton contains quarks, many people still keep a version of that image. They simply replace the solid nugget with a little container holding three smaller things. It is a sensible mental step. It is also, in the deeper sense, wrong. A proton is not a tiny hard ball. It is not a miniature bead with a smooth boundary and a quiet interior. It is not even best understood as a little box with three quarks sitting inside like passengers waiting for a train. The proton is a quantum system. It is active all the time. Its interior is not still. It is full of motion, exchange, field energy, and constant interaction. If the old picture of matter suggests neat layers of smaller and smaller objects, the proton is the point where that picture starts to give way. What lies inside is not a tidy arrangement of parts in the familiar ordinary sense. It is more like a structured storm. That does not mean chaos. Physics is not telling us the proton is random or lawless. Quite the opposite. The proton is governed by very exact rules, but it is not static, and it is not simple in the way our instincts first prefer. A more honest picture is that the proton is a bound state built from quarks and gluons, with continuous activity inside it, all held together by the strong interaction. The longer you look at it, the less it resembles a tiny object with a clean interior, and the more it resembles a living traffic pattern of energy and interaction. The first simplified description says the proton contains three quarks. That is true, and it remains true in an important sense. Those three are called the valence quarks. In the proton, they are two up quarks and one down quark. These are the quarks that set the proton basic identity. They account for its charge and distinguish it from the neutron. Without them, there is no proton in the ordinary classificatory sense. So the three-quark picture is not false, it is just incomplete. What makes it incomplete is everything else happening at the same time. The valence quarks are not sitting still in well-marked positions inside a little shell. They are part of a quantum state. They interact constantly by exchanging gluons, which are the carriers of the strong interaction. Those gluons are not occasional visitors. They are present throughout the structure. They carry energy, they carry momentum, and because they themselves carry colour charge, they interact not only with quarks, but with one another as well. This gives the proton an internal life that is far richer than the simple three-particle picture suggests. And then there is the sea. This is one of the most surprising features of the proton. In addition to the valence quarks, the proton contains a shifting population of quark-antiquark pairs that can briefly appear and disappear as part of the quantum dynamics of the strong force. These are called sea quarks. They are not permanent in the way the valence quarks are, but they are real parts of the proton state. They contribute to its behaviour. They are produced through the energy and interactions of the gluon field. and they make the proton a far more crowded and active place than early textbook diagrams usually imply. So already the old image of a proton as three tiny marbles has fallen apart. The proton is not three objects in a quiet container. It is three valence quarks embedded in a continuously interacting gluon field, with temporary quark-antiquark activity layered into that structure. That is why calling it a quantum storm is not dramatic for the sake of drama. It is a useful corrective. The proton is not still matter at the small scale. It is organized motion. This can be difficult to picture because the mind keeps reaching for everyday shapes. We like to imagine objects as having surfaces and interiors in the ordinary sense. We ask where exactly the quarks are, as though one might be on the left, one near the top, and one somewhere in the middle with a faintly apologetic expression. But that is not how quantum systems work. The quarks inside a proton do not have sharply defined little trajectories in the way planets orbit a star or peas rattle around in a tin. Their behavior is described in terms of quantum states and probability distributions. The proton does not contain tiny balls in precise locations. It contains a spread-out pattern of possibilities governed by the rules of quantum chromodynamics. That phrase can sound severe, but the meaning here is simple. If you ask where a quark is inside the proton, the answer is not a single fixed point. It is a distribution. The proton has structure, but not the kind of rigid mechanical structure that older intuition expects. This is one reason scattering experiments are so important. They do not give us a photograph of three neat dots. They reveal patterns that tell us how momentum and charge are distributed among the proton internal constituents. And what those patterns show is a dynamic system, not a small rigid body. Another way to see this is to ask where the proton mass comes from. If the proton were just three small constituents sitting together, you might expect its mass to be mostly the sum of the masses of those constituents. But that is not what nature gives us. The masses of the valence quarks by themselves account for only a small fraction of the proton total mass. Most of the proton mass comes from the energy of the strong interaction itself, from the motion of quarks, from the energy stored in the gluon field, and from the overall dynamics of confinement. This is one of the most important facts in the whole story. It means that the mass of ordinary matter is not mostly a pile of tiny little masses stacked inside protons and neutrons. It is largely the result of energy bound up in the strong force. The chair in a room, the floor under your feet, the body listening to this, all of that owes much of its mass to the restless internal energy of particles that look solid only from a distance. That is not a poetic exaggeration. It is one of the deep physical truths about visible matter, and it helps explain why the proton should not be imagined as a compact pebble. A pebble has most of its identity in its material substance as we casually understand it. The proton has much of its identity in its internal dynamical structure. Its mass, momentum distribution, magnetic properties, and spin all come from the collective behavior of quarks and gluons. The proton is not a passive container of ingredients, it is the result of an ongoing process. Spin is a particularly good example of how complicated this becomes. At first, you might imagine that if the proton is built from three quarks, then its total spin should simply be the sum of the spins of those quarks in some straightforward way. But experiments show that the quark spins alone do not account for the proton spin as simply as people once hoped. That led to a deeper investigation into the roles of gluon spin and orbital motion inside the proton. In other words, even something as basic as the proton overall angular character is not a neat one-line story. It emerges from several interlocking contributions within the quantum system. This is another sign that the proton is not a finished little lump. It is a bound state whose properties emerge from the whole internal pattern. When people say the proton is fundamental to ordinary matter, that is true in the practical sense, but inside the proton itself, there is nothing especially ordinary. It is not a miniature version of a grain of sand. It is more like a stable solution to a very complicated quantum problem. One useful historical shift here was the move from thinking of the proton only in terms of three quarks to thinking of it in terms of partons. That word was used to describe the point-like constituents seen in very high-energy scattering. Later, those partons were understood within the quark and gluon picture. At high energies, the proton can look like a swarm of constituents, each carrying some fraction of the proton momentum. Not just the valence quarks, but gluons and C-quarks too. This was a major clue that the proton interior is not simple. The higher the energy of the probe, the more richly structured the proton appears. This is one of the reasons proton collisions are so productive in modern experiments. A proton is not elementary. When two protons collide at very high energies, it is really their internal constituents that are interacting. Different quarks and gluons inside them can collide in different ways. That produces the enormous variety of outcomes seen in particle accelerators. If the proton were a small, solid sphere with no internal storm, the experimental world of high-energy physics would look far less interesting. Another important correction is about emptiness. Earlier, when people learned that atoms are mostly empty space, it became tempting to imagine that the nucleus was the place where true solidity finally lived. But once you enter the proton, even that confidence begins to slip. The proton has a size, yes, and it has a measurable spatial extent, but its interior is not filled with little hard material in the ordinary sense. It is filled with quantum fields and interactions. Solidity at the human scale is not made of tiny, solid things all the way down. It is made of forces, quantum states, exclusion principles, electromagnetic repulsion, and strongly bound hadronic structure. The deeper you go, the less the word solid behaves the way common sense wants. This does not mean the proton is vague or unreal. It means that reality at small scales is not built out of miniature ordinary objects. The proton has a real size. It has a real mass. It has real charge and real magnetic properties. But those properties belong to a system whose interior is governed by field dynamics, rather than by simple little bits arranged like furniture. A good way to hold this in mind is to stop picturing the proton as an object with contents, and start picturing it as a pattern that holds together. The pattern is stable enough that the proton can exist for an astonishingly long time, certainly long enough to serve as one of the foundations of all ordinary matter. But inside that stability is constant activity. The quarks are interacting. The gluons are carrying the strong force. C-quarks are appearing and disappearing. Momentum is being shared and reshaped. The proton is stable from the outside and restless on the inside. This can feel counterintuitive because stability usually suggests stillness to us. A building is stable because it stays put. A cup on a table is stable because it does not change much from moment to moment. But in physics, stability can arise from dynamic balance rather than from inactivity. The proton is stable not because nothing is happening inside it, but because the internal rules keep producing the same overall bound state. It is stable in the way a whirlpool can be stable, not because the water stops moving, but because the pattern persists while the internal motion continues. Even that analogy is only partial, but it points in the right direction. The proton is not dead still, it is steady through motion. This also helps explain why protons are so difficult to calculate in full detail from first principles. The theory behind them is known. Quantum chromodynamics tells us what the ingredients are and how they interact. But the low-energy bound state problem is hard because everything is strongly coupled. The quarks are not moving independently. The gluons are not a tiny correction. The whole structure is collective. Physicists use powerful numerical methods to compute proton properties from the underlying theory, and these efforts have been remarkably successful. But the very need for such heavy machinery tells you that the proton is not a simple object. It is a compact storm whose exact inner life is mathematically demanding. There is another reason the storm image matters. It helps fix the mistake people sometimes make when they hear that a proton has 3 quarks. They imagine the other details are unimportant decoration. But the gluons and C-quarks are not optional. In some ranges of momentum, gluons carry a huge share of the proton internal momentum. The proton is not mostly 3 quarks with a bit of force wrapped around them. It is a strongly interacting quantum system in which gluons play a central role. The three valence quarks define the identity, yes, but the full interior involves much more than three ingredients sitting in isolation. And all of this is happening inside something astonishingly small. That is worth pausing over. Every ordinary atom contains a nucleus, and every hydrogen nucleus is a proton. Every proton is a tightly bound quantum system with this rich internal activity. Matter does not merely rest on tiny pieces. It rests on tiny, ceaselessly active structures whose stability is achieved through powerful interaction. The calm, ordinary world is built from storms too small to see. There is a temptation at this point to say that the proton is mostly energy, but that phrase can become sloppy if it is not handled carefully. Everything with mass has energy. That is not special. What is special here is that the proton mass and character emerge largely from the energy of strong interaction dynamics, rather than from just adding up a few constituent masses. The proton is a bound state produced by quantum fields interacting intensely. That is the more precise way to say it, and once you say it that way, the image of a tiny billiard ball becomes impossible to keep. Even the boundary of the proton is not like the boundary of a grain of dust. A grain of dust has a physical edge in the familiar sense. The proton has a size that comes from how its charge and interaction distributions are spread out. Its boundary is more a matter of where those distributions effectively fade than a hard shell. Again, this is not vagueness. It is simply a different kind of physical reality from the one our senses evolved to handle. Human beings are not built to intuit quantum fields. We are built to avoid puddles and remember where we left the keys. All of this should leave us with a slightly different feeling about the visible world. Not awe in the soft, sentimental sense, but a more grounded correction. The material things around us are not built from tiny hard seeds of solidity. They are built from atoms, whose nuclei contain protons and neutrons, and those protons and neutrons are themselves dynamic quantum systems full of quarks and gluons. The stillness of a table is not stillness all the way down. It is an emergent calm built on relentless microscopic activity. And once you really accept that, the next question almost asks itself. If the proton is not a little box but a storm held together by the strong interaction, what happens when you try to tear that storm apart? What happens when you force the quarks farther and farther away, loading more and more energy into the gluon field? Because that is the next strange turn in the story. The proton does not simply open and spill its contents. Something more surprising happens instead, and it is there that confinement becomes impossible to ignore, because pulling too hard does not reveal isolated quarks, it changes the storm into new matter. If the proton is a tightly bound quantum system, rather than a little box of tiny contents, then the next obvious question is what happens when you try to force that system open. Not in the gentle way of a classroom diagram, where one simply draws three quarks with a bit of space between them and moves on, but in the physical sense. What really happens when you pull too hard? What happens when you strike a proton with so much energy that its internal quarks are driven apart with violent determination? Does the proton finally surrender its hidden pieces? Does one quark break loose and go flying off into the wider universe like a prisoner making a dramatic escape? Or does something stranger happen? By now you already know the answer in outline. Something stranger happens. The proton does not simply open and spill quarks into freedom. The strong interaction refuses that ending. The more you try to separate quarks, the more energy you pour into the binding field between them. That energy does not vanish. It does not politely weaken the connection and step aside. It builds. And once enough of it has built up, the system does something that would sound almost magical if it were not such a well-tested piece of physics. It uses that energy to create new quark-antiquark pairs. Instead of one isolated quark, you get new color-neutral particles. Instead of discovering a lone constituent, you produce more hadrons. This is one of the deepest corrections to the way people imagine fundamental particles. We're used to the idea that breaking things apart reveals smaller pieces. Smash a rock and you get fragments. Break a molecule and you get atoms. Split certain nuclei and you get smaller nuclei or free nucleons. Each stage feels like a kind of uncovering, but when you try to tear apart quarks inside a hadron, the process stops looking like uncovering and starts looking like transformation. The act of pulling does not just expose what was hidden, it changes the physical system into a new arrangement of matter. A useful place to start is with the field between quarks. In electromagnetism, the influence of charge spreads out in a way that becomes weaker with distance. The farther apart two electric charges are, the less strongly they affect one another. That is the pattern our intuition expects. The strong interaction does not behave that way once we move beyond extremely short distances. The colour field between quarks does not simply thin out and fade, it becomes concentrated. A common rough picture is that the field forms something like a narrow tube of energy between the quarks. The image is not exact, but it is helpful. If you pull the quarks apart, you stretch that tube. Stretching it stores more energy. So unlike the electric case, where separation weakens the interaction, here separation loads the system with increasing tension. That means there is no gentle road from bound quark to free quark. There is only a growing energetic cost. This is the heart of confinement in practice. The theory says quarks are confined, which can sound like an elegant abstract rule. But when you ask what that means dynamically, this is the answer. It means the energy required to separate quarks does not level off into success. It keeps rising until the system reaches a point where it is energetically favourable to create new particles, and because energy can become matter in quantum field theory under the right conditions, the field between the quarks can turn part of that stored energy into a quark and an antiquark. Once that happens, the original stretched connection breaks into two shorter colour neutral systems. The universe has avoided the forbidden lonely quark by making more company. If that sounds like a clever technical trick nature uses to get out of a difficult conversation, that is because in a sense it is exactly that. You ask for separation, and the strong interaction responds by rewriting the problem. It does not grant isolation, it grants creation. Let us slow that down and picture it carefully. Imagine a meson, which is a quark bound to an antiquark. If you somehow pull the quark and antiquark farther apart, the gluon field between them stores more and more energy. Eventually that energy becomes enough to create another quark-antiquark pair. Now instead of one stretched meson about to become two isolated particles, you get two shorter mesons. The original connection has not yielded freedom. It has split into fresh bound states. Something similar happens in more complicated hadronic systems as well. The details depend on the process, but the basic pattern is the same. Pulling hard enough gives you new hadrons, not exposed lone quarks. This is why particle detectors do not see free quarks arriving as isolated charge tracks with bizarre fractional electric charge. If quarks could exist alone in an ordinary observable way, detectors would sometimes register particles with those fractional charges. People have looked for such signatures very carefully. They do not appear. What appears instead is the outcome of hadronization, the process by which energetic quarks and gluons turn into ordinary hadrons, before they can be observed as separate objects. Hadronization is one of the key words in this part of the story. It is the name for the conversion of underlying quark and gluon activity into the hadrons that detectors actually record. In a high-energy collision, such as two protons smashing together at enormous speed, quarks and gluons inside the protons can collide very violently. For a brief moment, the process is described in terms of these elementary constituents, but as they move apart and the strong interaction takes over at larger distance scales, they do not remain as free quarks and gluons. They hadronize. They produce showers of mesons and baryons. The detector sees jets. Jets are one of the most striking signatures in particle physics. Instead of one isolated quark, you see a spray of ordinary particles moving in roughly the direction the quark originally took. These particles are the aftermath of confinement and creation working together. The underlying quark tried in a sense, to leave the scene, but the strong interaction forced the energy into new hadrons all along the way. So the quark reveals itself not as a lonely arrival, but as the organising cause behind a whole spray of final particles. This is a beautiful example of how physics often works at deep levels. The thing you want to isolate cannot be captured directly in the everyday sense, but its existence becomes unmistakable through the pattern it leaves. Quarks are not hidden because they are speculative. They are hidden because the theory that predicts them also predicts how attempts to isolate them fail. And those failures have a characteristic structure that experiments confirm again and again. There is an old habit in science education of presenting discovery as a story of peeling back layers until the secret centre is exposed. That is true up to a point. But here the peeling back starts to create fresh layers of its own. The proton is not a gift box that eventually opens to reveal 3 little labelled items inside. It is a bound state governed by a force that turns enough separating energy into more matter. The deeper layer is real, but it resists being presented in neat, isolated pieces. This resistance is not merely annoying, it is productive. The same mechanism that prevents isolated quarks also helps explain why matter is built out of stable hadronic states. If quarks could simply wander off freely, the world would look very different. Instead, the strong interaction channels its own intensity into structures. It binds, it confines, and when pushed too far, it creates. Creation here should be understood in the precise physical sense. We're not talking about matter appearing without cause. We are talking about energy stored in the field becoming particle pairs. Quantum field theory allows this. In fact, once you accept that particles are excitations of fields rather than little eternal pellets, the idea becomes almost natural. Fields contain energy. Under the right conditions, that energy can manifest as new particles, so long as the conservation laws are respected. The strong interaction makes heavy use of this possibility, because the field between quarks becomes so energetic when stretched. There is something almost economical about it. Nature does not spend energy tearing the last bond and releasing an isolated quark. It spends energy making new bound combinations. If you insist on pulling apart a hadron, nature sends you a bill in the form of more hadrons. This is also where one sees the practical distinction between binding and confinement. Many things in physics are bound but not confined. An electron is bound inside an atom, but it can be removed. A nucleon is bound inside a nucleus, but the nucleus can be broken apart. The binding energy is finite and separation can succeed. Quark confinement is deeper. The system does not offer a stable path to an isolated coloured object. Before that path can be completed, particle creation intervenes. Separation becomes multiplication. Now, there is a subtle point worth making. At extremely short distances and high energies, quarks behave almost as though they are less tightly bound. This is asymptotic freedom again. During the instant of a violent collision, a quark can act nearly free. But nearly free in that specific microscopic regime is not the same as free in the final observable outcome. The quark participates in the hard scattering as a constituent. Then, as the interaction unfolds and the products move outward, hadronization takes over. So the process has 2 faces. At the shortest scales, the theory lets quarks behave with a kind of temporary independence. At larger scales, the same theory forces the result back into bound hadrons. This is why high-energy experiments are both so revealing and so frustrating in the best possible scientific sense. They reveal the presence of quarks and gluons with remarkable clarity. At the same time, they deny us the simple visual satisfaction of catching one alone. Instead, they hand us jets, distributions, cross-sections, and event shapes. It is a language of patterns. But it is a very convincing language. Once you learn to read it, the quark world is everywhere in the data. One can also ask what this means for the concept of an object. In daily life, an object seems like something that can exist on its own. A spoon can lie on a table, a stone can sit in a field, a book can be placed on a shelf. even if these things are made of parts, each part can usually exist separately as a thing of its own. Quarks challenge that idea. They're ingredients of matter, yet not independent items in the observable world. Their physical reality is inseparable from the structures they inhabit and the interactions that bind them. That does not make them less real. It means reality at this level is relational in a very hard-nosed physical way, not in a vague philosophical one. To put it more plainly, a quark is not allowed to be lonely. That sounds almost humorous, and perhaps it should, because physics occasionally presents us with facts that are both exact and faintly absurd when translated back into everyday language. But behind the humour is a very sharp truth. The visible world is built from constituents that can only appear in combinations. Matter is not made from ultimate grains scattered independently through space. It is made from quantum entities whose strongest defining property includes their permanent confinement. You can see why this matters for the proton. If the proton were a simple little container, pulling on one quark should eventually remove it. Instead, the proton behaves more like a highly stressed field configuration that responds creatively to force. Push the system hard enough, and it does not reveal its innermost pieces. It makes new particles. The proton breaks, yes, but it breaks by transforming into further hadronic matter. This also helps explain why the strong interaction contributes so much to the mass of ordinary matter. The energy stored in these confining fields is not a minor detail. It is central to what hadrons are. The proton mass is largely the energy of the confined quark and gluon system, so when you pull too hard and the system creates new hadrons, you're seeing the same deep relation between energy, confinement, and matter that underlies the mass of the visible world in the first place. There is another experimental way this shows up. In collider events, one can often infer that a quark or gluon carried a certain amount of energy in a certain direction, but the detector records hadrons. Physicists then use careful theory and simulation to connect the measured jets back to the underlying partons, which is the collective term often used for quarks and gluons in this context. This whole enterprise works because hadronization is not random in the loose sense. It is complicated but statistically structured. The strong interaction hides quarks from direct observation, while still leaving enough order in the aftermath for us to reconstruct what happened. That is a subtle and rather generous arrangement. The universe refuses to hand over isolated quarks, but it leaves excellent clues, and yet there is one more wrinkle. If confinement is so strong under normal conditions, was it always like this? Was the universe from the very beginning a place where quarks were trapped inside hadrons? The answer is no. There was an earlier state, at temperatures and densities far beyond ordinary experience, where hadrons could not remain intact in the familiar way. Under those conditions, the strong interaction did not produce the same kind of separate proton and neutron structures we know now. Quarks and gluons existed in a different kind of medium, one that modern experiments can briefly recreate on tiny scales. So even though pulling too hard today creates more hadrons, there was a time when the universe itself was so hot and dense that the usual hadronic picture had not yet settled in. That next part of the story matters because it shows that confinement, though incredibly strong in the world around us, is not just a simple permanent prison wall in every circumstance. It is a feature of the universe as it cools and organises, and once you begin to ask what matter looked like before protons and neutrons formed as stable bound states, you step into one of the most fascinating moments in the history of the cosmos, when quarks and gluons move through a very different world than the calm atomic one we inhabit now. To understand the early universe when quarks roamed free, we have to be careful with the phrase roamed free, because it can suggest a neat picture that is still too ordinary. It might make you imagine lonely quarks drifting through empty space, the way dust floats in a sunbeam. That is not quite right. The early universe was not empty and calm with a few particles wandering about at leisure. It was dense, hot, violent, and packed with energy to a degree that is almost difficult to speak about without accidentally making it sound mythical. Quarks were not free in the quiet sense. They were deconfined in a seething medium, moving through a state of matter so extreme that the familiar particles of ordinary matter had not yet settled into existence in the way we know them now. That distinction matters because it helps us connect this early state to everything we have already discussed. We have spent a good deal of time learning that quarks cannot exist alone under normal conditions. We have seen that the strong interaction confines them into hadrons such as protons and neutrons. We have seen that when you try to pull quarks apart, the force does not simply relax and allow separation. It loads the system with energy until new hadrons are formed. So when we now say that in the early universe, quarks roamed free, we are not overturning all of that. We are talking about a period before the universe had cooled enough for ordinary hadrons to form as stable bound states. The rules of the strong interaction were still there, but the environment was so hot and dense that the usual confining structures had not yet taken over in the way they do now. A useful way to picture the early universe is not as a place in space, but as all of space in a very different condition from the one it has now. This is one of those points that often gets blurred in popular storytelling. The early universe was not a fireball sitting in an already existing room. It was the universe itself in an early state, hot everywhere, dense everywhere, with no ordinary empty backdrop waiting around outside it. That means when we talk about its temperature and contents, we are talking about the condition of everything that existed at that time, not just some region in which interesting events were happening. In the earliest instance that physics can describe with confidence, the universe was too hot for atoms, too hot for nuclei, too hot for protons and neutrons in the usual sense, and certainly too hot for anything like the ordinary matter around us now. The kind of structures we rely on in daily life had not formed. There were no atoms waiting to become chemistry, no molecules, no stars, no planets, no dust, no air, nothing that would satisfy our normal sense of matter. Instead, there was an intensely energetic plasma of elementary particles and radiation, all interacting rapidly, constantly, and without the stable layered structures that later became possible as the universe expanded and cooled. At some very early stage, the temperature was so high that quarks and gluons were not locked inside separate protons and neutrons. They existed in what physicists call a quark-gluon plasma. That phrase may sound technical, but the basic idea is not too bad. A plasma in general is a state of matter in which charged particles move more freely than they do in an ordinary neutral gas. In this case, the term refers to a hot dense medium, in which quarks and gluons are not confined into individual hadrons. They still interact strongly, in fact they interact intensely. But the usual hadronic boundaries have melted away. The medium behaves more like a collective fluid of quarks and gluons than like a gas of separate protons and neutrons. This is what is meant by deconfinement in the early universe. Quarks were not sitting inside individual protons because protons, as distinct stable bound states, had not yet formed in the familiar way. The thermal energy of the universe was simply too high. Any attempt by quarks to settle into ordinary hadrons was disrupted by the surrounding conditions. The whole environment was so energetic that the hadronic picture we use for the later universe did not apply in the same form. Quarks and gluons were part of a shared medium, colliding and exchanging energy constantly, with no peaceful opportunity for matter to cool into the stable particles that now build the visible world. This is one of the reasons the early universe is such a powerful setting for particle physics. It was not merely hot. It was a natural arena in which the deepest known ingredients of matter existed under conditions we can never produce on anything like a cosmic scale today. In our present universe, confinement dominates ordinary visible matter, but in the early universe, before enough cooling had occurred, the strong interaction manifested itself differently in practice. Quarks and gluons moved in a deconfined state because the ambient energy density was too great for hadrons to remain the primary stable form. Now, it is tempting to imagine this plasma as a sort of chaotic soup, and there is some truth in that as a first rough image, but it is worth improving the picture almost immediately. A quark-gluon plasma is not just random disorder. It is a highly interactive state governed by quantum chromodynamics. In fact, one of the surprises from modern experiments is that the quark-gluon plasma behaves less like a thin, disorganized gas and more like a strongly coupled fluid. It flows, it responds collectively, it has internal dynamics that show a kind of organized motion. That means the early universe was not simply a mess of loose particles crashing about in total chaos. It was a lawful medium with collective behavior, one whose details continue to teach physicists about the strong interaction under extreme conditions. As the universe expanded, it cooled. That sentence is simple, but it carries almost the whole plot of cosmic history. Expansion lowered the temperature and density. As that happened, different stages of matter became possible. This is the broad rhythm of the early universe. First, everything is too hot for stable structures. Then, as cooling proceeds, new forms of organization emerge. The period we are focusing on belongs to that larger pattern. There came a point when the quark-gluon plasma could no longer remain the dominant state. The universe cooled enough for quarks to become confined into hadrons. This transition is sometimes described as hadronization on a cosmic scale. Quarks and gluons that had previously belonged to the deconfined plasma became bound into protons, neutrons, and related particles. That moment was not just a technical shift in particle classification. It was one of the foundational transitions in the history of the universe. Once hadrons formed and stabilized, the road toward nuclei, atoms, stars, and everything else became possible. In that sense, the confinement of quarks is not just a feature of obscure subatomic theory. It is part of the reason the universe could become a place with durable matter at all. We should be clear here that the universe did not stop being violent the moment hadrons formed. Far from it. The early universe remained an extreme environment for quite some time by everyday standards. But the key point is that after this confinement transition, the basic building blocks of visible matter existed in a recognizable form. Protons and neutrons became meaningful physical actors. Later still, some of these would combine in nuclear processes. Much later, electrons would settle into atoms. Much later still, stars and galaxies would form. But the quark confinement transition was one of the great early acts in that long story of cooling and structure. There is an interesting irony in this. Today, the proton feels like a simple, familiar object in the basic language of matter. But in the early universe, the proton had not always won that status yet. There was a time before protons were the relevant, stable description of strongly interacting matter. This is another reminder that what counts as a natural physical object depends very much on conditions. At low enough temperatures and ordinary cosmic densities, hadrons are the natural units. At extraordinary temperatures and densities, the more natural description becomes a deconfined quark-gluon medium. Neither description is fake. Each belongs to a different regime of the same underlying physics. This also helps answer a subtle question. If quarks can be deconfined in the early universe, does that mean confinement is not really fundamental after all? The answer is that confinement is still fundamental to the low-energy world we inhabit. What changes is the state of matter under extreme conditions. The strong interaction remains what it is, but the thermal environment can alter whether hadrons are the right effective description. In the early universe, energy density was so high that the hadronic picture melted into the plasma picture. As cooling occurred, confinement reasserted itself in the familiar low-energy form. So the theory does not break. The dominant state changes with circumstance. One of the reasons physicists are so interested in recreating miniature versions of this early state in laboratories is that it offers a way to test our understanding of quantum chromodynamics in a regime that ordinary matter does not display. In collisions of very heavy atomic nuclei at extremely high energies, experiments can briefly create a tiny droplet of quark-gluon plasma. It does not last long, and it is unimaginably small, but it is enough to study. What is remarkable is that these droplets behave not like a weak dusty cloud of nearly free quarks and gluons, but like a dense fluid with surprisingly low viscosity. That result sharpened our picture of the plasma and reminded us that deconfinement does not mean non-interaction. The early universe plasma was still a strongly interacting system. This is important for imagination. Free in this context does not mean lonely and disconnected. It means not confined into individual hadrons. The quarks and gluons still influenced one another intensely. They were simply not locked into the separate proton and neutron structures that dominate the later cooler universe. So the early cosmos was not full of little solitary quarks taking independent strolls. It was full of a shared hot medium in which the usual hadronic walls had dissolved. And this leads to one of the deeper lessons of the whole subject. The forms matter takes are not eternal in the simple sense. Matter has phases. It has regimes. It changes what kind of structure is stable depending on the environment. Water can be ice, liquid, or vapor depending on temperature and pressure. That analogy is imperfect, but useful. The strongly interacting matter of the universe also has phases. In one regime, quarks are confined inside hadrons. In another extreme regime, they belong to a deconfined plasma. The underlying ingredients may be the same, but the stable collective form changes. The universe has a phase history, and the quark epoch was part of that history. There is also something wonderfully humbling in the timeline. The visible world now seems so full of long-lived structures that we can forget how delayed stability really was. The earliest universe was not quietly assembling familiar matter from the beginning. It had to cool through a series of thresholds before the kinds of objects we now take for granted could exist. The proton itself, so central to atoms and chemistry and life, belongs to a later calmer chapter than the quark-gluon plasma. Before the proton there was this more primitive and more extreme state of strongly interacting matter. That means every proton in the universe carries a history behind it. Not in the sentimental sense, but in a very literal physical one. It is a low-temperature survivor of a much hotter age. The same strong interaction that now keeps its quarks confined once participated in a cosmic medium where separate hadrons had not yet settled out. The proton is a product of the cooling universe. It is the stable descendant of a much wilder regime. We can also ask how quickly this transition happened. The answer, as so often in the early universe, is both fast and difficult to feel intuitively. On human timescales, the relevant changes happened astonishingly early and quickly. But the important point is not trying to emotionally grasp the exact interval. The important point is that the universe passed through this deconfined stage and then through the confinement transition very early in its history, long before atoms, long before light could travel freely without constant scattering by charged matter, long before stars, long before anything familiar. The quark epoch belongs to an era so early that the cosmos was still deciding what matter would even mean in its later recognizable form. This is why the early universe is often the only place where certain ideas in particle physics become cosmologically decisive, rather than merely subatomic curiosities. Quark confinement is not just about the inside of a proton in a laboratory. It is about a major transition in the first history of the cosmos. The way the strong interaction behaves determined when and how the universe moved from a deconfined quark-gluon state into a hadron-dominated one. That in turn helped set the stage for all later structure. There is another subtlety here. Even after hadrons formed, the universe still contained enormous numbers of particle interactions, particle-antiparticle pairs, and rapid transformations. The early cosmos was not instantly simplified, but the confinement transition changed the relevant language. Before it, one speaks naturally of quarks and gluons in a plasma. After it, one increasingly speaks of protons, neutrons, mesons, and the later nuclear processes involving them. The dominant units changed. The storm resolved into particles that could survive the cooling, and there is something profound about that change. The universe did not begin with the objects we now call matter in their finished form. It began with conditions under which those objects were not yet the stable answer. The familiar world emerged through a sequence of physical transitions. In that sense, the proton is not merely a component of matter, it is a historical achievement of the universe. This helps also with the phrase quarks roamed free. It is a useful phrase because it contrasts with confinement, but it should be held loosely. Quarks were deconfined as part of a dense, strongly interacting plasma. They were not free in the sense that an electron can be free in a beam. The early universe was too crowded, too hot, and too intense for that sort of isolated particle story. They moved in a collective medium. They were not trapped inside hadrons, but neither were they calmly independent little citizens of empty space. They were part of a cosmic fluid at extreme temperature, and that is both less simple and more interesting than the phrase free fur suggests. The modern effort to understand this state better continues to be one of the most exciting bridges between particle physics and cosmology. By studying heavy ion collisions and the behaviour of quark-gluon plasma in the laboratory, physicists are not merely learning about exotic droplets of matter, they are learning about a state the entire universe once passed through. That gives the subject a special kind of depth. The quark is not only a hidden constituent of the proton, it is also a witness to the earliest physical regime of the cosmos that our theories can meaningfully describe in this domain. So the world around us, with its atoms and molecules and familiar stable matter, exists only because the universe cooled enough for confinement to take hold and hadrons to form. The free-roaming age of quarks was not a lasting arrangement. It was an early phase, intense and collective, out of which the later matter-filled cosmos emerged, and that leaves us in a position to ask the final broad question of the whole journey. If quarks are so strange, if they can never exist alone in ordinary conditions, if the mass of matter depends so much on their confinement and the gluon fields around them, then what do quarks really tell us about reality itself? And why does their bizarre existence matter so much to the way we understand the universe? At the beginning of this journey, the word quark may have sounded like one more curious term from particle physics, memorable mainly because it does not sound like anything that should belong in serious science. By now it should feel less like a strange label, and more like a doorway into a very different picture of matter. A quark matters, because it is one of the basic constituents from which protons and neutrons are built. That alone would be enough to make it important. If you removed quarks from the universe, you would remove the hadrons that make atomic nuclei possible, and with them you would remove ordinary atoms, chemistry, stars in their familiar form, planets, rocks, oceans, living cells, and every calm solid object that seems so ordinary at human scale. Quarks matter because nearly all visible matter depends on them, but that is only the first level of why they matter. The deeper reason is that quarks change what it means to understand matter in the first place. They do not simply add one more layer under the proton, they force a correction to the way the mind wants to build the world. At first, the instinct is simple. Matter is made of objects. Those objects are made of smaller objects. Those are made of smaller ones still, all the way down, like a set of nested physical pieces. The quark seems at first as though it ought to fit that pattern. It sounds like one more little object waiting at the bottom of the stack, but once you look more closely, the familiar pattern begins to fail. The quark is not a tiny bead. It is not a little grain hidden inside the proton like a seed inside a fruit. It is a fundamental quantum entity with definite properties, but one whose existence in the observable world is inseparable from confinement and interaction. That is one reason quarks matter so much. They tell us that the deepest known ingredients of visible matter are not independent little stones lying at the foundation of reality. They are part of a theory in which the force between them determines whether they can ever show up separately at all. That is a profound change in perspective. We usually think of forces as things that act on already existing objects. Gravity acts on planets. Electromagnetism acts on charges, a push acts on a box. But with quarks and the strong interaction, the force is not merely something added after the fact. It helps decide what kinds of separate physical objects are available in the first place. The proton exists as a stable hadron because the strong interaction binds quarks into a colour-neutral state. The isolated quark does not exist as an ordinary free object because that same interaction prevents it. The relationship is not secondary, it is part of the thing itself. This says something important about reality. It says that at the deepest scale we currently understand for visible matter, nature is not built from little independent units that just happen to associate with one another. Instead, some of its basic ingredients are defined through the structures they form and the fields they inhabit. In everyday life, independence feels like part of what it means to be a thing. A cup sits by itself. A stone can be picked up and moved. A spoon can lie on a table without needing the table in order to count as a spoon. Quarks challenge that habit of thought. They are real, measurable, indispensable, and yet they do not stand alone. Their strange existence suggests that separateness is not the deepest default of the physical world. At least in this domain, structure and relation are built in from the start. That might sound philosophical, but it is also very practical. The mass of ordinary matter depends on it. One of the most surprising facts we encountered is that the mass of the proton does not come mainly from adding up the bare masses of its three valence quarks in the naive common sense way. Most of the proton mass comes from the energy of the quark and gluon system, from confinement, motion, and the strong interaction itself. That means that the weight of the ordinary world owes much of its existence to the restless dynamics inside hadrons. The floor under your feet, the walls around you, the body listening to this, all of it derives a great deal of its mass not from tiny hard kernels of matter, but from energy stored in an intensely interacting quantum system. That is an extraordinary statement, and it is one of the clearest examples of why quarks matter. They are not only ingredients of matter, their behaviour helps explain why matter has the mass it does. If quarks were simple little particles loosely placed inside protons, the visible world would be a different kind of place. Instead, because quarks are confined by gluons in a strongly interacting system, the proton becomes a dynamic object whose mass emerges from that interaction. So quarks matter because they are part of the reason the world is heavy enough to be the world we know. They also matter because they reveal how misleading ordinary language can be when science goes deep enough. Nearly every major word in this subject invites misunderstanding at first. Particle sounds like a tiny pellet. Flavour sounds culinary. Colour sounds visual. Spin sounds mechanical. Force sounds like a push. Field sounds like open countryside. None of these words fully means what everyday experience first assumes. Quarks teach us that the world can be precise without being intuitive. A theory can be exact, predictive, and experimentally successful, while still resisting the kinds of pictures that come naturally to creatures who evolved to deal with apples, doors, weather, and misplaced socks. This is not a failure of science. It is one of its most impressive successes. Science keeps going even when intuition runs out. It builds a language of experiment, theory, and disciplined inference that can describe realities our senses were never designed to handle directly. That is another thing quarks say about reality. They say the universe is not obligated to be built in ways that fit the visual imagination of the human mind. The inside of a proton is not a little solar system. The quark is not a tiny ball. The strong interaction is not just a stronger version of a familiar force. Reality at small scales is stranger than common sense, but it is not chaotic. It is orderly in a deeper and more demanding way. Quarks matter because they show us the difference between what feels understandable and what actually is understandable once the theory and evidence are good enough. There is also the history of discovery itself. Quarks matter because they are a triumph of science not only as a body of knowledge but as a method. No one looked into a proton with a tiny camera and saw three quarks lined up neatly. Quarks were inferred through patterns, through scattering experiments, through the structure of hadrons, through the success of quantum chromodynamics, and through decades of collider data that consistently behaved as though quarks and gluons were the correct underlying description. This is a useful reminder that science often knows hidden things, not by direct ordinary sight, but by the disciplined reading of consequences. We know the wind exists from movement. We know the inside of stars from light and spectra. We know quarks from the patterns they leave in matter and collisions. Their strange existence says that reality is often accessible by inference, long before it is accessible to any picture the imagination finds comfortable. And then there is confinement, which may be the strangest and most revealing feature of all. A quark matters not only because it exists, but because its inability to exist alone is a clue about what kind of world we live in. It would have been easy to imagine that the deepest ingredients of matter must be the most freely isolatable ones. Instead, nature gives us the opposite. The deepest ingredients of visible matter are locked into combinations by a force that grows more resistant when separation is attempted. Pull too hard and you do not uncover a free quark. You create new hadrons. That is a remarkable statement about the architecture of the world. It means that reduction does not always end in display. Sometimes it ends in transformation. There is something almost instructive in that. The universe does allow us to investigate its structure. It allows us to infer quarks, to measure their effects, to use them in theory with astonishing success. But it does not always grant the simple visual satisfaction of isolating every constituent as a standalone object. In that sense, quarks matter because they teach restraint. They remind us that understanding is not the same thing as turning everything into a collection of little pebbles on a tray. Sometimes understanding means accepting a deeper level of law, in which the pieces are real but not separately available in the ordinary sense. Quarks also matter because they connect the tiny and the enormous. We often divide science into the very small and the very large, particle physics on one side and cosmology on the other, as if they were neighbouring countries with different languages. But quarks sit right on the border between them. Their behaviour is essential to the proton and neutron. The proton and neutron are essential to nuclei. Nuclei are essential to the chemical elements. The elements are essential to stars, planets, and life. And in the early universe, before protons and neutrons had fully taken over as the stable form of strongly interacting matter, quarks and gluons existed in the quark-gluon plasma from which the later hadron world emerged. So when we talk about quarks, we are not talking about something tucked away beneath reality. We are talking about something whose properties helped shape the history of the universe itself. This is one reason the subject has a certain quiet grandeur. The same theory that explains why a quark cannot appear alone in a detector also helps explain a major transition in the first moments of cosmic history. The strong interaction confined quarks into hadrons as the universe cooled. That means the later existence of atoms depended on the earlier history of quark matter. The story of quarks is therefore also part of the story of why there is a stable, visible universe at all. Their strange existence says that cosmic history is written not only in galaxies and expansion, but in the behaviour of quantum fields inside particles. They matter as well because they reveal the layered character of explanation. At one scale, chemistry is enough. At another, atomic physics is needed. At another, nuclear physics. Then hadron physics. Then quarks and gluons. None of these layers makes the others useless. A chemist does not need to compute quantum chromodynamics to understand how salt dissolves in water. A bridge engineer does not need to model sea quarks inside protons to know whether a support beam will hold. The higher layers remain valid and useful, but quarks show that deeper layers can change the meaning of the higher ones without destroying them. The atom was not wrong. It was incomplete. The proton was not wrong. It was incomplete. This is a healthy lesson in how science works. Reality can be described successfully at many levels, but the deeper levels sometimes reveal that the apparent simplicity of the higher ones rests on something much stranger. That too says something about reality. It says the world is not arranged for a single perfect description at one obvious scale. It is structured. Different levels of organisation matter. A proton is real as a proton. It is also real as a quark and gluon-bound state. Both descriptions are true in their proper domains. Quarks matter because they deepen rather than erase the objects above them. They tell us that understanding is often a matter of learning when each level of description is the right one. There is also the question of mystery. Quarks have been enormously successful in theory and experiment, yet they do not answer everything. Why are there 6 flavors? Why 3 generations? Why the mass pattern we observe? Why these coupling strengths? The Standard Model describes quarks with magnificent accuracy, but it does not finally explain why the universe selected exactly this arrangement. In that sense, quarks matter because they mark the edge between what we know very well and what we still do not know. They are not signs of scientific failure, they are signs of scientific maturity. We know enough to ask better questions now. Their strange existence says that explanation in physics is powerful, but not finished. This is often underappreciated. When people hear that science has a theory of quarks, they sometimes imagine the subject is complete and settled in the trivial sense, as though all that remains is the paperwork. But the existence of quarks opens questions as much as it closes them. Why this family? Why confinement in exactly this form? What deeper framework, if any, sits beyond the Standard Model? The fact that quarks are so well established and still so conceptually rich is part of what makes them matter. They are both a solved success and an unsolved invitation. On a more human level, quarks matter because they stretch the imagination without breaking the discipline of science. They give us a picture of matter that is genuinely strange but not vague. That distinction is valuable. It is easy to drift into grand language whenever physics becomes unfamiliar. But quarks do not need fog around them to be interesting. The interest is already there in the facts. A basic constituent of matter that cannot be isolated. A proton whose mass comes largely from internal interaction energy. A force whose carriers carry the very charge they mediate. A world in which the visible calm of matter rests on the confinement of quarks and the exchange of gluons. None of this requires exaggeration. Reality is already done enough, and perhaps that is what quarks say most clearly about reality. They say the world is more structured than it first appears, more relational than common sense expects, and more dependent on hidden dynamics than surface appearances suggest. The table seems solid and still. The proton inside it is a quantum storm. The proton seems like a basic unit. It is made of quarks and gluons. The quark seems like it should be a tiny object you could isolate. It cannot exist alone. The pattern continues downward, not into nonsense, but into a form of order that asks more of the mind than ordinary seeing does. That does not make the world alien in the dramatic sense. It makes it layered and patient. The ordinary world remains what it is. Water still pours, light still falls through a window, a room still grows quiet at the end of the day, but beneath that calm, matter is not simple. It is built from structures whose deepest parts obey rules that do not resemble the world of human scale. Quarks matter because they make that hidden depth undeniable. There is even a kind of comfort in that, though not the sentimental sort. It is the comfort of a world that is stranger than it looks and yet deeply lawful. Quarks do not appear alone, but their absence as isolated particles is not arbitrary. It follows from the same theory that explains the proton, the neutron, jets in colliders, the behaviour of the quark-gluon plasma, and the mass of hadrons. The strangeness is not loose, it is coherent, and that coherence is one of the most satisfying things science can offer. It tells us that even when reality stops looking familiar, it has not stopped making sense. So why do quarks matter? They matter because without them there is no ordinary matter in the form we know. They matter because they explain the proton and neutron at a deeper level. They matter because their confinement helps generate the mass of visible matter. They matter because they connect particle physics to cosmic history. They matter because they reveal that forces can help determine what kinds of separate objects exist. They matter because they show that the universe is not built from tiny familiar beads, but from quantum entities whose identities are tied to interaction, field, and law. And what does their strange existence say about reality? It says that the world is not obliged to line up with intuition. It says that independence is not always the deepest form of existence. It says that hidden structure can be more important than visible appearance. It says that matter, at its foundation, is dynamic rather than inert, relational rather than isolated, and exact without being picturable in the old simple way. It says that the universe can be perfectly real and thoroughly strange at once. By the time you return to the proton after all this, it no longer feels like a simple dot at the heart of the atom. It feels like a crowded, active, deeply bound state whose constituents can never simply step outside. And by the time you return to the ordinary objects around you, they too feel slightly different. Not unreal and not magical, just deeper. More contingent on hidden order. More dependent on quantum events that never announce themselves at human scale. The world stays familiar, but the familiarity thins just enough to let the underlying structure show through. So perhaps the lasting impression of quarks is not just that they are tiny or strange, but that they are an example of how far reality can depart from the pictures the mind first offers, while still remaining precise, testable, and beautifully consistent. That is why they matter. And once that idea settles in, even the quietest ordinary piece of matter begins to look less like an ending, and more like a very successful arrangement of deeper things still at work inside it.